Welcome to the opening chapter, where we explore the Databricks Certified Data Analyst Associate exam and the fundamental concepts of the Lakehouse architecture. You are about to embark on a structured path that turns cloud-based data complexity into actionable business intelligence. This is an unofficial, independently produced course. It is not affiliated with, endorsed by, or connected to Databricks in any way. All trademarks belong to their respective owners. This content is for informational and educational purposes only and does not guarantee a passing grade on the certification exam. Building a career as a certified Databricks data analyst requires moving beyond mere spreadsheet proficiency toward mastering unified data platforms. This course is designed to transition you from a functional user to a certified professional by focusing on the core competencies demanded by the exam. We will systematically bridge the gap between traditional data warehousing workflows and the modern lakehouse paradigm. You will discover how to articulate the business value of Databricks, navigate the workspace interface with precision, and apply best practices for data management. By the time you complete this course, you will possess the technical rigor, conceptual clarity, and strategic insight required to pass the certification exam. We prioritize hands-on proficiency and architectural understanding, ensuring that you can speak the language of Databricks confidently in any professional setting. This is your comprehensive guide to mastering the ecosystem and formalizing your expertise. The Databricks Lakehouse architecture represents a fundamental shift in how organizations store and process data. Traditional data warehouses were designed for structured data in proprietary formats, which often created silos and prevented the use of advanced machine learning tools. Conversely, data lakes provided flexibility for unstructured data, but lacked the necessary governance, performance, and reliability features of relational systems. The Lakehouse combines these strengths by implementing a high-performance query engine on top of low-cost object storage, while layering in ACID transaction support through Delta Lake. This architecture allows data analysts to run complex SQL queries against massive datasets without the overhead of moving data between separate environments. By providing a unified platform, Databricks effectively eliminates the barrier between the data engineer, who prepares the data, and the analyst, who extracts the value. At the heart of the Lakehouse lies the Delta Lake format, which provides the reliability that modern analytics requires. ACID compliance is perhaps the most significant feature, ensuring that transactions finish completely or not at all, which keeps your data consistent even when many users access it simultaneously. Schema enforcement prevents low-quality, malformed data from corrupting your tables, while time travel allows you to query historical versions of your data for audit or debugging. These features shift the focus of the job from manual data cleaning to high-level analysis. Furthermore, the Medallion architecture organizes data into distinct layers to drive progressive refinement. The bronze layer acts as the raw intake, the silver layer provides a cleansed and filtered version, and the gold layer fulfills specific business-level requirements. Understanding this hierarchy is essential for passing the certification exam, as it dictates how data flows within the platform. Successful preparation for the Data Analyst Associate exam necessitates a deep understanding of the Databricks SQL persona. The exam evaluates your ability to navigate the workspace, manage SQL warehouses, and write efficient queries across various data objects. We will dedicate significant time to setting up the SQL warehouse, which is the compute resource responsible for executing query requests, as choosing the correct size and type directly impacts performance and cost. You must become familiar with the interface layout, including the query editor, dashboard creation tools, and the data explorer. The exam consists of a series of multiple choice and multiple response questions, usually administered within a strict time limit. We will focus on the specific domains covered by the exam, ensuring you are comfortable with the nuances of Unity Catalog, visualization tools, and query optimization techniques. To begin our practical work, you must ensure your environment is correctly configured to match the exam requirements. This involves setting up your initial SQL warehouse, which serves as the compute cluster for all your analytical workloads. You will learn to provision these resources, adjust scaling policies, and monitor usage metrics. These configuration steps are not merely about aesthetics. They are critical to understanding how Databricks controls costs and performance. As you configure your environment, pay attention to the relationship between the workspace and your underlying cloud storage providers. We want to ensure you are comfortable moving between internal schema management and the external data connections common in real-world deployments. This practical foundation will prepare you for the more complex task of managing data lifecycles and security settings throughout the remaining modules. I look forward to our next session. Welcome to this chapter, where we will examine the configuration of SQL warehouses to ensure your compute strategy aligns with performance requirements. We will cover the distinctions between warehouse types and how to optimize them for your specific workloads. In the ecosystem of Databricks, the SQL warehouse acts as the computational engine responsible for executing the queries you write within the SQL workspace. Unlike general-purpose clusters, these are specifically tuned for concurrent SQL workloads, interacting directly with the Delta Lake storage layer. Understanding how these warehouses function is fundamental, because improper configuration often leads to either wasted budget or unacceptable latency. You have three primary tiers at your disposal, which are Classic, Pro, and Serverless. Each of these serves a distinct purpose depending on whether your priority is cost management, advanced feature accessibility, or rapid compute availability. Choosing the right tier is the first step in building a reliable data analysis pipeline that scales according to your business needs. When we look at the serverless SQL warehouse, it is difficult to overlook the operational benefits derived from its design. With serverless, Databricks manages the compute resources on your behalf, effectively abstracting away the underlying virtual machines that would otherwise require manual intervention. The most immediate advantage is the startup time, which is measured in seconds rather than minutes, as the compute is already provisioned and ready for your specific query submission. This architecture is particularly compelling for ad hoc analysis, where users expect a responsive experience without waiting for a cluster to spin up. Furthermore, the auto-stop feature on serverless is significantly more aggressive, ensuring that you do not pay for compute capacity that sits idle during periods of low activity. By minimizing the time to first query and automating maintenance tasks, you effectively convert operational overhead into time for actual data analysis. Classic and Pro warehouses offer a more traditional experience, where you retain more control over the infrastructure, though this comes with the trade-off of higher management complexity. Pro warehouses are positioned as the middle ground, providing access to more advanced functionalities like improved performance and built-in query federation capabilities that are not always available in the Classic tier. The sizing of a warehouse, ranging from XXS up to 4XL, is a critical variable that dictates the number of worker nodes assigned to your compute cluster. A larger warehouse size is not necessarily the solution for every performance bottleneck, as scaling up primarily helps with complex, heavy queries that benefit from increased RAM or CPU power. It is essential to monitor your workload concurrency, as adding extra capacity via scaling out is often more effective for managing multiple concurrent users than simply choosing the largest possible individual size. The scaling parameter is where you define the minimum and maximum scaling boundaries for your clusters, often referred to as auto-scaling. When multiple users submit queries simultaneously, Databricks can automatically spin up additional clusters to handle the load, preventing the queuing effect that degrades user experience. You must analyze the concurrency patterns of your organization to set an appropriate maximum limit. Balance responsiveness against potential cost spikes. Remember that each additional cluster brings its own set of resources. So while it solves your concurrency issues, it also creates more throughput and consumption on your billing account. Setting an informed auto-stop duration is the final lever in your control, as this shuts down the compute once the activity ceases. A shorter auto-stop is usually better, but you must ensure it does not interrupt users who are merely taking a temporary break during their analysis sessions. Monitoring your compute resource utilization is not a one-time setup task, but a continuous cycle of observation and adjustment. Within the Databricks SQL console, you can view the query history, which provides insight into which queries are consuming the most resources and whether your current warehouse size is sufficient. If you observe that your queries are consistently hitting memory limits or executing slowly, that is a clear indicator that you may need to reconsider your sizing tier. Conversely, if your utilization metrics show that you are paying for large clusters that consistently sit at low CPU usage, you are over-provisioning your infrastructure. By keeping a close eye on these metrics, you align the technical reality of the warehouse with the business value provided by your data initiatives. This iterative refinement process is what distinguishes a proficient data analyst from someone who simply accepts default settings. See you in the next lecture. Welcome to this chapter, where we will focus on mastering the Databricks SQL Workspace and your primary tools for data analysis. We will walk through the interface to ensure you can navigate, manage objects, and monitor query performance with confidence. If you are aiming to pass the Databricks Certified Data Analyst Associate exam, understanding the SQL Workspace is not just about knowing where buttons are located. It is about knowing how to be productive in a professional environment. This course provides the most streamlined approach to mastering these mechanics, ensuring you transition from an occasional user to an expert who can navigate the platform efficiently. We will cover the layout of the SQL editor, deep dives into asset management, and the crucial workflows for data discovery that you must know to succeed in this certification. By the end of this journey, you will possess the practical skills required to manipulate data at scale while adhering to industry-standard best practices. Investing your time here is the single best way to ensure you are ready for the rigorous demands of the certification exam. When you first land in the Databricks SQL Workspace, the primary interface you interact with is the SQL editor. Think of the SQL editor as your primary workbench where you draft, execute, and refine the queries that power your analytical pipelines. On the left side of the screen, you will find the schema browser, which is an essential tool for data discovery because it allows you to explore catalogs, schemas, and tables without leaving your workspace. When you select a specific table, you can view the column names and data types, which helps prevent time-consuming typos while writing joins or aggregate functions. The editor itself supports syntax highlighting and auto-completion, which are designed to make your development process faster and less error-prone. Once you run a query, the results are displayed immediately below the editor in a dynamic grid, allowing you to preview the returned dataset before you commit to further processing. Managing your work happens within the asset browser, where you must distinguish between personal folders and workspace-wide shared assets. Your personal folder serves as a private sandbox, where you can draft experimental queries or refine complex logic in isolation before they are deemed production-ready. Once your SQL scripts are finalized, you can save them as queries, which can then be organized into folders to maintain a logical structure for your team's projects. The shared workspace folder is where collaborative assets live, and effective management here requires an understanding of how permissions interact with your specific environment. When you save a query, you are essentially creating a bookmark for your logic that can be reused in dashboards or external tools, provided that you have properly configured the underlying SQL warehouse. This workflow ensures that your organization maintains a single source of truth for its core analytical logic. Monitoring the performance of your queries is an essential part of the data analyst role, particularly when dealing with large data sets or complex transformations. The Query History tab offers a comprehensive view of all executed operations, including those triggered by automated processes or other members of your team. In this view, you can identify long-running queries by looking at the execution duration and status indicators, which helps you pinpoint bottlenecks in your SQL code. If a query is taking longer than expected, you can click on its execution ID to open the query profile, which provides a detailed breakdown of how the data was scanned and processed. This feedback loop is vital for optimizing your work, as it allows you to see how your choice of filters, joins, or functions impacts resource consumption. By regularly reviewing this history, you gain a better intuition for how your SQL interacts with the underlying storage and compute layers of the Lakehouse architecture. Within the broader Databricks ecosystem, the SQL persona serves as the dedicated interface for analysts, separating the SQL-centric tasks from the notebook-based experimentation used by data scientists. While you might be familiar with the data science workspace, switching to the SQL persona narrows the scope of the navigation bar to tools specifically tailored for data warehousing and dashboarding. This shift is intentional because it removes unnecessary complexity, allowing you to focus entirely on querying and report generation tasks. You will find that the integrations with SQL warehouses happen seamlessly here, as the interface is inherently tied to the compute resources required to run your high-performance queries. As an analyst, your success often depends on your ability to utilize this persona effectively to maintain clean, organized, and performant assets that others can rely on. Always verify that your active warehouse has the necessary capacity before running broad, data-intensive queries to ensure that you are not underpowered during peak analytical hours. See you in the next lecture. Welcome to this new chapter where we will demystify the core storage mechanics of the Databricks Lakehouse, specifically focusing on Delta Lake and its ASDA guarantees. We will break down how this storage layer functions to provide reliability in distributed systems. To understand Delta Lake, we must first look at its foundation, which relies on Parquet files. Parquet is a columnar storage format that is highly efficient for analytical queries because it allows engines like Spark to skip unnecessary data through predicate pushdown and column projection. However, Parquet by itself is just a collection of files in a directory. It lacks the metadata required for transactional consistency. Delta Lake acts as the abstraction layer on top of these files, maintaining a transaction log that records every change made to the table. This log, often referred to as the Delta log, is an ordered sequence of JSON files that store information about which files were added, which were removed, and the overall state of the table at any given time. When you perform a write operation, the system does not modify existing Parquet files in place, as that would be unsafe in a distributed environment where multiple readers and writers might be active. Instead, it creates new files and records the transaction in the log, effectively ensuring that the table remains in a consistent state even if a failure occurs mid-operation. The acronym ACID stands for atomicity, consistency, isolation, and durability. And these are the pillars that make Delta Lake fundamentally different from traditional file-based data lakes. Atomicity ensures that a transaction is all or nothing. If a write job fails, the transaction log is never updated to include the incomplete changes, leaving the table exactly as it was before the attempt. Consistency means the data adheres to the rules defined for the table, such as schema constraints, throughout its lifecycle. Isolation is managed through optimistic concurrency control, which assumes that multiple writers rarely interfere with each other. If two processes try to update the same partition concurrently, one will succeed and the other will fail the commit, forcing it to retry. Durability is achieved because once a commit is acknowledged as successful by writing a new entry to the Delta log on persistent storage, the data persists regardless of system crashes or power failures. This architecture transforms the unreliable nature of distributed cloud object storage into a robust, database-like experience for data analysts and engineers alike. One of the most powerful features enabled by this transactional logging is time travel, which allows you to query the state of your data as it existed at a previous point in time. Because every change is versioned in the log, you can access older versions of a table by using specific syntax, such as using the timestamp as off clause in your SQL queries. This is invaluable for troubleshooting data quality issues or reproducing analytical results from a specific reporting period, even if the current data has moved on. Furthermore, Delta Lake provides mechanisms to govern data structure through schema enforcement and schema evolution. Schema enforcement acts as a gatekeeper, rejecting any write operations that attempt to insert data with columns not present in the existing table definition, which prevents accidental data corruption. Conversely, schema evolution allows you to safely update the table schema to accommodate new requirements, such as adding a new column to a pipeline without having to rewrite the entire historical dataset. Understanding the balance between these two is essential for maintaining a clean, performant, and reliable data warehouse. Optimizing your interaction with these tables requires an understanding of how these concepts translate into real-world query patterns. When writing complex pipelines, prioritize schema enforcement to ensure upstream changes do not break downstream reporting assets unexpectedly. If you find that your data structure must change, use the explicit evolution features to signal that change in a controlled manner rather than disabling the safety checks entirely. Keep in mind that while time travel is a powerful tool, maintaining historical versions consumes storage space, which is why regular maintenance tasks like vacuuming are necessary to remove old files no longer needed by the current table state. By mastering these foundational storage concepts, you gain the ability to provide not only analytical value, but also technical assurance that the data backing your dashboards is precise and technically sound. This level of control is what makes the Lakehouse architecture a significant evolution over legacy data lake implementations. See you in the next lecture. Welcome back. Let's dive into the practical application of the Medallion architecture within a Databricks environment. The Medallion architecture is less a rigid set of rules and more a logical progression of data refinement designed to solve the inherent entropy of raw data streams. Often referred to as the multi-hop architecture, it imposes a structural discipline on your data lake, which is essential when you move from ad hoc exploration to production-grade analytics. By segregating data into bronze, silver, and gold zones, you create a tangible lineage that allows you to trace business insights back to their raw origins with verifiable confidence. This separation of concerns is not merely for organization. It is a fundamental strategy for managing data quality, schema evolution, and performance optimization in a lakehouse environment where the same table often serves both raw ingestion and high-stakes BI reporting. At the bronze layer, often called the raw zone, your primary objective is to capture data exactly as it arrives from source systems. Since we are dealing with high-velocity ingestion, this layer should store data in its original format, frequently using an append-only pattern to preserve history. You should treat the bronze layer as an immutable record of all incoming events, meaning you rarely, if ever, delete records here. Because this layer acts as the foundational source of truth, it is wise to maintain low schema enforcement to avoid failing ingestions due to upstream source changes. Storage formats here often leverage Parquet for efficiency, though the structure remains largely untyped or minimally flattened to allow for flexible downstream processing. Moving into the silver layer represents the transition from a data dump to a data asset, where cleaning, transformation, and validation occur. This is where you enforce schema constraints, remove nulls, handle duplicates, and normalize your data structures to support analytical queries. Unlike the pure ingestion approach of the bronze zone, the silver zone should be treated as a curated set of tables that represent individual business entities. This is the stage where you perform inner joins to create coherent records, apply data quality checks, and ensure that your formats are optimized for read-heavy workloads. Since Delta Lake provides ISID transaction capabilities, you can safely perform merge operations here to update existing records based on primary keys while maintaining consistency throughout the pipeline. The gold layer is the final destination for business-ready information, specifically designed for aggregation, reporting, and high-performance BI consumption. Here, you often move away from the normalized structures found in the silver layer toward denormalized, star schema designs like fact and dimension tables. Performance in the gold zone is paramount, so you might choose to implement partition column strategies or liquid clustering if your dataset requires rapid filtering across large time-based ranges. Business logic and KPIs are pre-computed in this layer, effectively shielding your end users from the complexity of the raw data processing pipelines. By creating these views or tables, you enable data analysts to build dashboards without having to understand the underlying intricacies of how the raw data was ingested or cleansed. From a design perspective, identifying the right storage format and schema is as much about operational efficiency as it is about data utility. Using Delta Lake for all three layers is highly recommended because it provides the underlying transaction logs, time travel, and robust schema enforcement needed to handle technical failures gracefully. When designing the physical storage, strive to align your partition strategies with the most common query patterns identified in your downstream BI dashboards. If you find your gold tables becoming bloated, it is an indication that you should push more aggregation logic back into the pipeline rather than performing heavy calculations at query time. Remember that each jump between the medallion layers should provide tangible value, whether that value is improved data quality, performance, or accessibility for your business stakeholders. By implementing this architecture, you cater to two distinct audiences: data scientists, who often require the high-fidelity access provided by bronze and silver, and business analysts who require the efficiency and speed of the gold layer. This duality is the hallmark of a mature data platform, allowing the organization to scale without creating silos. When your data is treated as a product moving through these refined stages, the reliability of your BI reports increases because the transformation logic is centralized rather than duplicated across various analysts' workbooks. This structured approach is the backbone of reliable analytics on Databricks, providing a predictable lifecycle for every byte of data entering your system. See you in the next session. Welcome back. In this chapter, we explore the mechanics of robust data ingestion, specifically focusing on the copy into command for your Lakehouse pipelines. When we transition from manual data loads to automated production pipelines, the primary challenge is achieving idempotency. Idempotency ensures that running the same ingestion process multiple times does not result in duplicate records or inconsistent states within your destination delta table. The copy into command is designed specifically for this purpose in Databricks, providing a declarative way to load data from cloud object storage such as AWS S3, Azure Data Lake Storage, or Google Cloud Storage. Unlike a standard insert statement, copy into tracks which files have already been processed by maintaining a history of loaded files within the metadata of the target table. This mechanism allows you to point the command at an entire directory, and Databricks will identify only the new, unprocessed files since the last execution. To leverage this command, you start by defining the target table and the source path from which data should be pulled. The flexibility of copy into is quite impressive because it natively supports a variety of file formats, including CSV, JSON, Parquet, and Avro. You simply specify the file format in the From clause and provide additional options using the File Format Options parameters. For instance, if you're ingesting CSV files, you can define the delimiter, whether headers exist, and how to handle null values directly in the query. This means you do not need to rewrite your ingestion logic every time the upstream source changes their file naming convention or compression format, provided the schema remains compatible. Configuration of source options requires careful attention when permissions or security boundaries are involved. You often need to supply credentials or assume a specific IAM role to access the underlying cloud storage account. These credentials can be passed securely using temporary tokens or by referencing external locations managed within the Unity catalog. Error handling during these bulk loads is equally critical because real-world data is rarely pristine. You can configure the command to ignore corrupted files or limit the number of data errors allowed before the entire process aborts, which saves significant time during debugging. The ability to specify a pattern for file discovery also helps in scenarios where directories contain mixed content or archived data you wish to ignore. Comparing this approach to other ingestion methods is essential for understanding when copy into is the right architectural choice. If you require a predictable, batch-oriented ingestion process, copy into is often superior to a standard insert into select statement because it manages the state check internally. While autoloader is better suited for continuous streaming ingestion scenarios that scale automatically, copy into is perfectly adequate for scheduled batches where you want simpler operational overhead. It strikes a balance between low maintenance and high reliability, ensuring that your Medallion architecture remains performant without requiring complex custom scripting for tracking file lineage. By relying on the built-in metadata, you spend less time building plumbing and more time refining the actual analytical models that bring business value. See you in the next lecture. Welcome back to our discussion on data ingestion strategies within the Databricks Lakehouse, where we will now focus on the powerful capabilities of autoloader. When we deal with data arriving in cloud storage, such as Amazon S3, Azure Data Lake Storage, or Google Cloud Storage, the classic approach of periodically listing directory contents often hits a wall. This is particularly true as the volume of files grows into the millions, as the sheer cost and latency of exhaustive metadata listing operations become prohibitive. Autoloader introduces the Cloud Files format, a specialized streaming source that transforms how we ingest data, making it incremental and highly scalable. Instead of scanning an entire bucket, Autoloader can subscribe to cloud provider notification services to identify new files as they land, which drastically reduces compute overhead. Alternatively, it can perform targeted directory listings when event notifications are impractical or unavailable, maintaining a stateful record of what has already been processed to avoid redundant ingestion tasks. The mechanism by which Autoloader tracks file discovery relies on two modes, namely directory listing and file notification. In the directory listing mode, the engine keeps a persistent key value store to remember which files it has already ingested, which ensures that an incoming stream only processes new data. When you configure Autoloader to use file notifications, Databricks automatically manages the creation of notification queues, such as AWS SQS or Azure Event Grid, to receive real-time updates about new file write events. This is the preferred method for high-throughput scenarios because it turns the ingestion process into a reactive system rather than a polling-based one. Using these notifications allows your data pipeline to remain lightweight and responsive without needing to crawl through nested directory structures repeatedly. One of the most compelling features of Autoloader is its ability to handle evolving data structures, a common pain point in modern data engineering. By default, Autoloader employs schema inference, which samples the incoming data files at the start of the stream to automatically determine the column names and data types. As your upstream data producers inevitably change their outputs, perhaps by adding a new column or changing an existing one, Autoloader supports automatic schema evolution. This means the engine can detect these structural changes and update the target delta table definition without manual intervention or pipeline downtime. By defining schema hints, you can guide this inference process even when data is messy or inconsistent, providing a balance between fully automated discovery and precise control. Setting up an autoloader stream is syntactically clean, leveraging the standard Spark structured streaming API while replacing the typical file format with the Cloud Files provider. You simply point the read stream to your storage path, specify the Cloud Files configuration, and let the system handle the complexities of checkpointing and state management. Because the underlying data is stored in Delta Lake format, you receive the full benefits of ACID transactions during the write process, ensuring that your data remains correct even if a stream is interrupted or restarted. This combination of autoloader and Delta tables allows you to maintain a reliable, up-to-date view of your cloud storage in a Medallion architecture without orchestrating complex manual batch windows. See you in the next lecture. Hello, welcome back. In this lesson, we will explore the mechanisms for managing external cloud storage connections within the Databricks Unity Catalog framework. When we transition from internal managed tables to data residing in your own cloud infrastructure, the primary concern shifts to authentication and authorization. Unity Catalog introduces a structured way to handle this via storage credentials and external locations. A storage credential is an object that encapsulates the long-lived cloud identity, such as an AWS IAM role or an Azure Service Principal, required to access the underlying storage provider. By decoupling the cloud identity from the specific file path, we achieve a more granular governance model, where an administrator can grant access to specific storage buckets without revealing the root credentials to every contributor. This abstraction is fundamental to maintaining a secure perimeter around your data lake, ensuring that only mandated principals have the privilege to interact with the raw cloud bytes. Think of the storage credential as a key that opens the front door of your cloud container, while external locations act as specific rooms you are permitted to enter. Without this intermediary layer, managing access would require broad, difficult-to-audit permissions that inevitably weaken your security posture over time. Many of you might be familiar with the legacy approach of mounting cloud storage buckets directly to the Databricks file system. While mounting was once the standard, Unity Catalog has essentially superseded this pattern by encouraging the use of direct URI paths combined with defined external locations. When you use an external location, Databricks resolves the path at the catalog level, which means the underlying data remains under the jurisdiction of Unity Catalog governance policies. If you continue to use deprecated mount points, you bypass the centralized security controls that define the Lakehouse experience, effectively creating a blind spot in your data lineage. Direct URI access allows the Unity Catalog engine to inspect and audit every read or write request, ensuring that your metadata reflects exactly what is happening in the physical cloud storage. This is a critical distinction for any organization aiming to pass compliance audits because the audit trail in Unity Catalog is unified and immutable. By preferring external locations over mounts, you align your architecture with modern best practices that prioritize security and visibility above proprietary convenience. The choice between managed tables and external tables further complicates the governance conversation, but it remains a decision based on the desired data lifecycle. A managed table is one where Databricks holds both the metadata and the actual data files under the default root storage of the workspace. If you drop a managed table, the data itself is physically deleted from storage because the platform owns the entire entity. Conversely, an external table points to data that resides in an external location of your choosing, governed by the storage credentials we discussed earlier. When you drop an external table, only the metadata in the metastore is removed, leaving the actual data intact in your cloud bucket. This is useful for scenarios where different systems or applications outside of Databricks need to access the same underlying files concurrently without interference. Understanding this persistence boundary is essential for the exam, as it determines how you design your storage strategy to handle data retention and cleanup operations. The relationship between your cloud service provider and the compute clusters is mediated by the Unity Catalog service, which validates your identity before dispatching the request. Whether you are running on AWS with S3, Azure with ADLS Gen 2, or GCP with GCS, the workflow remains consistent throughout the platform. Databricks compute resources utilize the storage credential to assume the requested identity and perform the necessary storage operations on your behalf. This mechanism ensures that the compute cluster never needs persistent administrative credentials stored in its own configuration files. Consequently, the surface area for potential security breaches is significantly reduced because the credentials are managed centrally within the Unity Catalog metastore. This centralized approach allows for immediate revocation of access should an identity or a compute resource be compromised. As a data analyst, you should view this hierarchy not as a technical hurdle, but as a robust safety net that empowers you to work with external data sources with confidence in your institutional security. I will see you in the next lecture. Welcome back. In this chapter, we will master the essential maintenance tasks required to ensure your Delta tables perform efficiently and remain cost-effective within your Lakehouse architecture. Building a robust data platform requires more than just moving data into tables. It requires a disciplined approach to maintenance and lifecycle management. Throughout these lessons, we will explore how to use administrative commands such as optimize and ZORDER to reorganize your data for peak query performance. We will also dive into the vacuum command to understand how to prune stale files and manage the implications this has for data retention and time travel. Furthermore, we will examine how to audit table states using metadata commands and how to properly configure table properties to suit your specific analytical workloads. Mastering these concepts is not just about passing an exam, but about becoming a practitioner who knows how to maintain a high-performance environment. This chapter covers the technical internals of Delta Lake storage that every analytical professional must understand to optimize costs and speed. Managing the lifecycle of a Delta table starts with understanding how data is physically laid out in your cloud storage. When you perform frequent insert or update operations on a Delta table, you often end up with a large number of small, fragmented files, which places unnecessary strain on the storage layer and slows down read queries. The optimize command addresses this by compacting these fragmented files into larger, more efficient files, essentially performing a merge operation that preserves the transactional integrity of the table. By default, this reorganization improves parallel read performance because the underlying engine can scan fewer files to retrieve the required data. You should treat optimize not as a one-time setup, but as a recurring maintenance task integrated into your data pipelines. When you run this command, it merely reorganizes the physical files without changing the logical contents visible to your SQL queries, ensuring that existing applications continue to function without disruption. While Optimize consolidates files, the ZORDER technique takes organization a step further by performing multi-dimensional clustering on columns that are frequently used in your where clauses. When you apply ZORDER to a column like a high cardinality customer identifier or a time series timestamp, Databricks maps the data in such a way that related values are physically co-located in the same set of files. This allows the query engine to use data skipping, where it can completely ignore the bulk of your storage during a scan because it knows the desired value cannot possibly be in those specific files. It is important to note that ZORDER is most effective when applied to columns that have a high number of distinct values and are regularly filtered against. If you apply it to a low cardinality column, such as a Boolean flag or a status code, you will likely see diminishing returns for the additional computation time required. Balancing the CPU cost of these optimization commands against the performance gains for your end users is a key skill for any data analyst. Data lifecycle management also involves the inevitable removal of data that is no longer required for time travel or audit purposes. Delta Lake maintains a transaction log that tracks every change made to a table, which is what enables the time travel feature to query older versions of your dataset. However, every time you update or delete data, the old files remain on your cloud storage provider to satisfy the retention policy. The vacuum command is the mechanism provided to physically delete these stale files that are no longer referenced by the current version of the table. By default, vacuum will not delete files younger than 7 days because doing so would break the ability to perform time travel or restore the table state within that window. You must exercise caution when setting the retention threshold, as once files are removed by vacuum, they cannot be recovered by the Lakehouse engine. To effectively audit your environment, you must become comfortable with the metadata commands that Databricks provides. The describe detail command provides a comprehensive view of your table, including its location, the number of files, the size on disk, and the creation timestamp, which is essential for capacity planning and troubleshooting. When you need to understand the evolution of your table, describe history gives you access to a chronological list of transactions that have impacted the data, showing you the timing, the operation type, and the user who performed the action. These commands are invaluable during the debugging phase of a data engineering project, or when verifying whether an optimization job has actually completed as intended. By combining these visibility tools with your maintenance commands, you gain a transparent view into the storage layer. This level of insight allows you to maintain clean, performant, and correctly versioned tables throughout their lifecycle. See you in the next lecture. Welcome back. Let us discuss how to effectively leverage ANSI SQL standards and common table expressions to structure complex analytical workflows within Databricks. This chapter will sharpen your ability to write modular, readable, and highly maintainable queries, which is essential for any professional data analyst. When we interact with the Databricks SQL environment, we are essentially operating within a robust implementation of ANSI SQL. While specific proprietary extensions exist, adhering to standard SQL syntax ensures your logic remains portable and predictable across different layers of the lakehouse. One of the most significant shifts in modern query construction is the move away from deeply nested subqueries toward the cleaner, more declarative syntax of common table expressions, often called CTEs. A subquery, particularly when nested several levels deep, eventually becomes a cognitive burden, forcing the reader to jump back and forth between internal parentheses to understand the data flow. By contrast, a CTE allows you to assign a name to a results set before you consume it, effectively turning a what into a how that reads from top to bottom. This stylistic choice is not merely about aesthetics, it is about reducing the surface area for logic errors. When you define a transformation as an isolated CTE, you can test it independently to ensure the intermediate results match your expectations before joining it to subsequent tables. Syntactically, a CTE begins with the with clause, followed by the alias and the query definition, which is then immediately available to the main statement below it. If you need to perform multiple transformations, you can chain multiple CTEs by separating them with commas, creating a clear pipeline of data refinement. Unlike traditional views, which persist in the metastore, CTEs exist only for the life of the query, making them perfect for transient analytical calculations that do not need to be reused elsewhere in the database. From a performance perspective, Databricks Query Optimizer is highly efficient at handling CTEs, often materializing or inlining them depending on the computational cost and the complexity of the execution plan. You should favor CTEs over subqueries because they offer a superior way to document your intent, essentially serving as a form of self-documenting code. Many analysts find that when they look back at a query written with nested subqueries 6 months later, it takes significant effort to reconstruct the logic, whereas a well-named CTE acts as an explanatory variable for the dataset. Beyond basic aliasing, CTEs unlock the power of recursion, which is a specialized technique for handling hierarchical data, such as organizational charts or bill of material structures. A recursive CTE consists of an anchor member, which determines the initial dataset, and a recursive member, which references the CTE itself to build subsequent levels of the hierarchy. While you might not use recursion in every analytical scenario, knowing how to implement it correctly within Databricks allows you to solve graph-based problems that would otherwise require complex UDFs or external procedural code. When working with large datasets, remember that recursion should be scoped carefully to avoid infinite loops or excessive memory consumption. Always ensure you have a termination condition defined within the recursive member to keep your query footprint within the bounds of your SQL Warehouse instance. This level of declarative control is precisely what defines a senior analyst who understands not just how to get an answer, but how to architect a solution that remains resilient as data volumes scale. In scenarios where you need to perform row-level logic against other tables or functions, lateral joins offer a distinct advantage over standard SQL operations. A lateral join acts something like a for-each loop in a programming language, where the right-hand table expression is evaluated for each row processed in the left-hand table. This is incredibly useful when you need to calculate a top-end value per category or when you're working with set returning functions that need to be correlated to the outer row context. If you find yourself struggling with a nested query that cannot see the columns in its outer scope, a cross or outer apply, or the ANSI standard cross-lateral, often solves the problem by providing the necessary correlation. Combined with set operations such as union, which combines result sets while removing duplicates, or intersect, and except, which handle the overlapping and exclusive data portions, you gain a complete toolkit for advanced set theory applications. Using union all is generally preferred for performance if you know your data is distinct, or if you explicitly want to keep duplicates, as it skips the overhead of deduplication that the engine performs during a standard union. To ensure your code remains optimized for the Databricks engine, always consider the readability of your SQL structure as an extension of the data's quality. When you present your work to collaborators, the clarity of your CTEs demonstrates a disciplined approach to modeling that translates well into documentation. Maintainability is the primary metric by which long-term data projects are measured, so prioritize writing queries that others can easily audit. By adopting these standard patterns, you ensure that your analytical pipelines remain robust, even as the underlying data schemas continue to evolve. Focus on building these modular blocks, and you will find that even the most complex analytical requests become manageable sequences of logical steps. See you in the next lecture. Welcome back. In this lesson, we explore window functions, a critical tool for performing complex analytical calculations over sets of rows related to the current row. When we analyze time series data or perform cohort analysis within the Databricks SQL environment, standard aggregate functions often fall short because they collapse the result set into fewer rows. Window functions solve this by allowing us to maintain the granularity of our original data while simultaneously calculating values like running totals, rankings, or period-over-period changes. To define a window, we use the over clause, which serves as the bridge between standard query logic and the specific scope of the calculation. Within this clause, we use partition BI to divide our result set into partitions, much like a group by operation, but without reducing the row count. Crucially, the order by clause within the window definition specifies the logical sequence of rows within those partitions, which dictates the results of functions that depend on order, such as rankings or cumulative sums. Ranking functions are perhaps the most common entry point into this topic, and it is vital to distinguish how they handle ties in your data. Row number provides a unique, sequential integer to each row based on the defined order, which is perfect for deduplication tasks where you only want the most recent record per entity. Conversely, rank assigns the same number to tied records, but leaves gaps in the sequence, meaning if two items are tied for second place, the next rank will be fourth. Dense rank also assigns identical numbers to ties, but it does not skip subsequent values. So the next rank after a pair of seconds would be third. These distinctions matter significantly when building operational reporting pipelines where business logic dictates how to account for duplicate timestamps or identical transaction amounts within a dataset. For time series analysis, we frequently rely on the lead and lag functions to compare a current record's value with its predecessor or successor. Imagine you are tasked with calculating the daily delta in revenue. Instead of performing a self-join, which is computationally expensive and syntactically verbose, you simply define a window partitioned by a store ID and ordered by date. Using lag, revenue 1, allows you to pull the previous day's figure directly into your current row's calculation, facilitating instant comparisons without altering the broader dataset shape. This approach is highly efficient for calculating growth rates or identifying trends over time because the engine can evaluate these positions during the scan phase of the query execution. By avoiding joins, we significantly reduce the shuffle overhead, which keeps our SQL warehouse resources focused on compute rather than data movement. To gain full control over cumulative calculations, we must understand the window frame specification, which defines exactly which rows are considered relative to the current one. By default, the window frame ranges from the beginning of the partition to the current row, which is exactly why a simple sum, column, over, partition by category, order by date, results in a running total. However, we can explicitly control this using the rows or range keywords to create rolling windows, such as a moving average of the last 7 days. A frame defined as rows between 6 preceding and current row tells the engine to look only at the set of 7 records ending at the current row, effectively sliding the calculation window as the query progresses. Proper management of these frames is essential for performance on large-scale datasets, as expansive frames require the engine to keep significantly more data in memory during the aggregation phase. When working within Databricks SQL, we should be mindful that these performance implications scale with our compute size and the volume of data stored in our Delta tables. While window functions are highly optimized internally, partitioning by very high cardinality columns can lead to skewed data distribution if the volume of rows per partition is wildly inconsistent. Always consider if your partitioning strategy allows the engine to distribute the workload effectively across all available nodes in your SQL warehouse. When we combine these windowing techniques with the underlying performance of Delta Lake, we create robust analytical pipelines capable of processing petabytes of data while keeping query latency predictable. Mastering these concepts ensures that you can present sophisticated metrics to stakeholders with the confidence that your SQL logic is both accurate and resource efficient. I will see you in the next lecture. Welcome back. In this chapter, we will master the intricacies of complex joins and set operations to build robust data models. Joining tables is a fundamental operation, yet it remains one of the most significant sources of performance degradation in distributed systems. When we perform an inner join, we essentially filter the Cartesian product of two tables based on a predicate, keeping only rows with matching join keys. Left and right outer joins extend this by including rows from one side even when no match is found, filling the missing columns with null values. A full outer join is the most inclusive, preserving data from both sides, which is often required in complex reconciliation tasks. However, these operations trigger data movement across the cluster, specifically the shuffle exchange, where data is redistributed across worker nodes based on the hash of the join key to ensure parity. Understanding how the query optimizer handles these shuffles is crucial for performance. Databricks provides specific hints to control how these joins are executed, primarily through broadcast joins. When one table is significantly smaller than the other, it is often more efficient to broadcast the smaller table to all worker nodes. By doing so, we avoid the heavy reshuffling of the larger dataset, as every node has access to the comprehensive subset of the broadcasted data. If the optimizer does not automatically detect this, you can force it using the broadcast hint. However, this is not a panacea, as broadcasting excessively large tables will lead to out-of-memory errors on executors. Always rely on the query profile to verify whether the optimizer actually honored the broadcast hint or discarded it due to size constraints. Data skew is another frequent challenge when dealing with large-scale joins. This phenomenon occurs when a small number of keys are associated with a disproportionately large amount of data compared to other keys in the table. During a shuffle, these skewed keys are sent to a single executor, causing that node to become a bottleneck while others sit idle. Effectively managing skew often involves salting your data, which means adding a random suffix or prefix to the join keys to distribute the load more evenly across the cluster. While this adds complexity to the logic, it prevents the dreaded long-tail latency where one task takes orders of magnitude longer than the rest to complete. Beyond standard joins, anti- and semi-joins are essential tools for filtering datasets based on the presence or absence of records in another table. A left semi-join returns rows from the left table where a match exists in the right table without duplicating rows from the left, even if multiple matches are found. An anti-join, conversely, returns rows from the left table where no match exists in the right. making it ideal for identifying orphaned records or data anomalies. These joins are highly performant because they do not require returning the actual columns from the join table, only the existent status. Using these effectively reduces the volume of data processed in subsequent stages of your pipeline. In the context of star and snowflake schemas, we often encounter many-to-many relationships that conflict with the clean, hierarchical structure of these models. While traditional dimensional modeling advocates for star schemas, real-world business data rarely fits perfectly into these shapes. To resolve many-to-many relationships, we often introduce bridge tables, which allow us to perform cascaded joins to navigate the schema. This requires a precise understanding of join sequences to avoid fan-out issues, where the row count explodes due to unintentional Cartesian products. By keeping the fact table as the central point and utilizing dimension tables for filtering, you keep your analytical queries performant and your results consistent. Set operations such as union, intersect, and except provide a different way to manipulate your data subsets. Union all is generally preferred over union because it avoids the costly distinct operation of removing duplicate rows. When you use intersect or except, you are essentially asking the engine to perform set comparisons, which forces data shuffling to compare rows across partitions. Just like with joins, these operations are heavy on the network and compute resources. Always assess if you can achieve the same outcome using a left anti-join instead of except, as the optimizer might find a more efficient path for a join than for a standard set operation. Practical application of these joins is the hallmark of a skilled data analyst. Whether you are dealing with sparse data or massive fact tables, the goal is always to reduce the amount of data moving across the network. By observing the query profile and understanding the physical execution of your SQL statements, you can make informed decisions about when to use hints or how to refactor your data model to minimize long-running tasks. Remember that your SQL code is not just a definition of results, but a blueprint for how the cluster should distribute and combine information. Consistent results depend on this architectural clarity. See you in the next lecture. Welcome back. Today we examine the specific mechanisms Databricks provides for working with semi-structured JSON data within a SQL environment. In modern data engineering, it is common to encounter data that does not fit neatly into a rigid, tabular schema. JSON is the lingua franca of this semi-structured world, often arriving as opaque string blobs in external storage. Databricks allows us to query these structures directly using dot notation, which is the most ergonomic way to access nested fields. If you have a column named raw data containing a JSON object, you can reach into it by typing raw data user ID. This colon-based syntax effectively treats the JSON path as an object hierarchy, allowing you to extract specific values without needing full schema definitions up front. It is a powerful form of schema on read that provides immediate visibility into incoming data before you invest the effort to structure it permanently. When your requirements move beyond simple extraction, you will need the formal utility functions. The getJSOnObject function serves a similar purpose to colonization, but is often useful when the path is provided as a dynamic string variable. More importantly, when dealing with transformations, from JSON allows you to convert a JSON string into a structured SQL type by providing a specific schema definition. This function is essential when you need to perform relational operations, such as filtering or aggregating fields that were previously hidden inside the raw string. Conversely, JSON allows you to serialize structured data back into a JSON string, which is useful when preparing data for downstream systems that expect web-native formats. These functions create a bridge between the fluid nature of raw ingested data and the rigorous requirements of a well-modeled data warehouse. Handling arrays within JSON payloads requires a strategy for normalization, as relational databases prefer flat rows over nested collections. The explode function is the primary tool here. It takes a column containing an array and projects a new row for every element found within that array. This effectively turns a single parent record with multiple children into a set of individual records. If your JSON structure is deeply nested and contains multiple layers, you might find yourself needing to call multiple explosions or, more elegantly, Use the flatten function if dealing with nested arrays. By converting these nested collections into vertical structures, you allow standard SQL grouping and counting operations to function as intended. This process of unnesting is a critical phase in the Medallion architecture when moving data from a raw, bronze state to a more refined, silver state. Schema on-read offers incredible flexibility, but it places the responsibility for data validation squarely on the query designer. Since the underlying JSON may vary, your queries must be robust enough to handle missing keys or unexpected types. If a field is missing, the colon syntax typically returns a null value rather than failing the entire query, which is a design decision that protects your analytical pipelines from crashing. However, you should still consider using schema enforcement or evolution strategies when writing these records to Delta tables to avoid long-term technical debt. When you define a schema explicitly, you gain performance benefits, as the engine can prune data more effectively during scan operations. Choosing between the speed of ad hoc colon syntax and the reliability of explicit schema definitions is a strategic decision that depends on your specific performance and governance requirements. See you in the next lecture. Welcome back. In this lesson, we will explore the power of higher-order functions in SQL for manipulating array data directly within Databricks. When we handle semi-structured data, we often encounter arrays that contain nested elements. Historically, developers have relied on exploding these arrays into separate rows, performing transformations, and then aggregating them back together. This approach is rarely efficient, as it inflates the volume of processed data and introduces unnecessary complexity in query design. Higher-order functions allow us to bypass this unnesting pattern by applying logic directly to the collection. Think of a higher-order function as a mechanism that takes a primary expression and a lambda function as input to produce a new result. By adopting this paradigm, we treat the array as a discrete object that flows through our pipeline without losing its structural identity. The transform function is perhaps the most fundamental tool when you need to modify the contents of an existing array. It operates by iterating over every element in the array and applying a lambda expression to produce a corresponding output element. For instance, if you have a column containing a list of prices in one currency, you can use transform along with an exchange rate multiplier to generate a new array of converted prices in a single statement. Because the function preserves the original array structure, the relationship between the index of the input element and the output element remains consistent. This predictability is essential when you are performing data cleaning or mapping raw input values into standardized formats before they reach your reporting layer. Beyond simple transformations, we often need to refine our datasets based on specific criteria without discarding the entire record. The filter function serves this purpose by evaluating a Boolean predicate against each array element. Only elements that satisfy the condition are retained in the resulting array, effectively pruning the collection of unwanted values. Consider a scenario where you have a log of user interactions stored as an array of timestamps, but you only care about events that occurred after a specific date. By using filter, you keep the array structure intact while discarding only the entries that fail your temporal constraint, which is significantly more performant than a join or a lateral explosion. When we need to verify the existence of specific values within a collection, the exists function provides a concise solution. Instead of writing complex subqueries or joining against reference tables just to check for a single matching item, we define a predicate that identifies the desired element. This function returns a Boolean true if at least one element in the array satisfies the condition provided by the lambda expression. It represents a shift from imperative scanning to declarative identification, which align perfectly with the SQL philosophy of describing what data we need rather than how to navigate the underlying storage to find it. Replacing a massive left join with an exist check on an internal array can often lead to substantial improvements in query compilation times. Complexity often arises when we need to compute a scalar value from an array, such as summing total sales from a nested list of transaction items. The reduce function facilitates this by accumulating values starting from an initial seed state. You provide an expression that dictates how each element is combined with the current accumulator value as the engine iterates through the array. This allows for powerful analytical operations like calculating a running total or concatenating string values within a nested object. By mastering this function, you encapsulate logic that would otherwise require multiple procedural steps into a clean, expression-based query. The primary advantage of these functions is the reduction of cognitive load when maintaining your codebase. When you avoid the sprawl of lateral views and nested subqueries, your intentions become much more visible to anyone reading your queries. We move away from the noise of structural manipulation and focus squarely on the business logic being applied to the data. Databricks SQL behaves optimally when it can process these operations at the engine level without breaking the data into row-level operations, as this allows for better parallelization and utilization of the underlying cache. As you build more sophisticated analytical models, leverage these functional patterns to maintain performant and readable data transformations. I will see you in the next lecture. Hello, welcome back. In this session, we will explore how to use materialized views and streaming tables to optimize data processing and query performance within the Databricks Lakehouse. When we talk about performance acceleration in the context of a data analyst role, we often encounter the bottleneck of repeated, complex computations that scan vast amounts of data. A standard SQL view is merely a stored query that executes every time you reference it, meaning it provides no storage-level optimization or compute pre-calculation. In contrast, a materialized view physically stores the result set of a query as a table, which allows you to trade a small amount of storage for significant gains in read latency. This is particularly useful when you need to serve data to dashboards that require sub-second response times, as the underlying heavy lifting has already been performed during the last refresh cycle. By delegating this logic to the Databricks engine, you ensure that end users are not waiting for the system to recompute historical aggregates from the raw data layer on every page refresh. Understanding the refresh mechanism is critical because it dictates how effectively your data reflects the most current state of the source. Materialized views leverage Databricks Delta Live Tables infrastructure to track changes and perform incremental computation, which is far more efficient than a full recomputation of the entire dataset. When upstream source data changes, the system determines the delta, the minimal set of records affected, and updates the view accordingly. This approach minimizes the compute footprint and reduces the associated costs of running complex pipelines. However, one must remember that while a materialized view is performant, it is eventually consistent by definition because it requires an execution trigger, whether that is manual or scheduled, to bring it back in sync with the source. Streaming tables introduce a different paradigm by treating data as a continuous flow rather than a static batch, which is essential for low-latency BI consumption. Unlike a standard table that you might load via a batch job, a streaming table is designed to ingest data from an external source as it arrives, providing a virtually real-time window into your gold layer. When you integrate streaming tables into your Medallion architecture, you're essentially setting up a pipeline that processes the incoming data stream into a polished, structured format suitable for consumption by reporting tools. This allows analysts to build dashboards that reflect current operations without the inherent delay of traditional overnight batch processing cycles. It is a powerful pattern to deploy when your business stakeholders demand rapid visibility into incoming transactional events. We must remain clear about the distinction between these objects and standard storage tables or views regarding resource utilization. A standard view is computationally ephemeral, consuming no persistent storage for data, but demanding CPU cycles whenever accessed. A materialized view resides on disk, so you incur storage costs, but the query becomes significantly cheaper and faster to execute repeatedly. This trade-off is almost always favorable when the query frequency is high and the logic involves costly joins or complex window functions. If you find yourself repeatedly executing the same expensive query to feed a visualization tool, moving that logic into a materialized view is a clear indicator of architectural maturity. Configuring these assets correctly requires an understanding of your specific query patterns and the volatility of the source data. If your data changes infrequently, a scheduled refresh for your materialized view is usually sufficient to maintain relevance without wasting compute resources. For scenarios necessitating higher frequency, you should evaluate if a streaming approach provides a better balance between cost and freshness. The goal is to move the heavy lifting away from the user's query time and into the managed refresh cycle of the Lakehouse. By mastering the distinction between these artifacts, you position yourself to deliver data products that are both stable and incredibly responsive under load. I will see you in the next lecture. Welcome back to our exploration of advanced analytical patterns within the Databricks Lakehouse environment. In this session, we investigate data modeling best practices, focusing on the trade-offs between architectural purity and query performance. When we construct schemas within a Lakehouse environment, we must acknowledge that, while the underlying storage is scalable, the way we structure our tables influences the cognitive and computational load of our consumers. Traditional dimensional modeling, such as star schemas, remains incredibly influential here because it minimizes join complexity for end users who interact with the SQL warehouse. We often grapple with the decision between normalization, which reduces redundancy and protects data integrity, and denormalization, which favors read-heavy analytical workloads. In a typical Databricks setup, the performance gain from avoiding complex joins often justifies a degree of controlled denormalization, especially when aiming to satisfy BI tool requirements. You should leverage surrogate keys to decouple your analytical layer from the volatility of source system identifiers, ensuring your downstream models remain stable even when upstream business logic changes. Managing these keys effectively requires a disciplined approach to ingestion, often utilizing delta tables to maintain consistency across the Medallion architecture. Implementing change tracking is a fundamental aspect of maintaining an accurate historical record, and this is where slowly changing dimensions become indispensable. SCD Type 1 implies that we override existing records to reflect the current truth, which is useful when history is not required or when correcting erroneous data entries. Conversely, SCD Type 2 preserves history by adding new rows and utilizing versioning flags to indicate the active record, allowing us to perform point-in-time analysis. In Databricks, the merge into statement manages these operations with transactional guarantees, meaning you can synchronize source data with your destination tables without fear of partial updates. By combining a predicate that checks the natural key with specific versioning or timestamp comparisons, we ensure that Type 2 dimensions remain readable and performant. This declarative approach to data manipulation is far superior to procedural scripts, as it allows the query optimizer to plan the most efficient execution path for your upserts. An often overlooked aspect of schema design in the Databricks ecosystem involves the proper application of constraints, specifically primary and foreign keys. While it is worth noting that Databricks does not enforce these constraints in the same way traditional RDBMS systems do, they serve as vital metadata for the cost-based optimizer to perform query pruning and join reordering. When you declare that a column serves as a primary key, you are effectively providing a hint to the optimizer that it can expect unique values, which helps in simplifying join conditions. Furthermore, providing this documentation helps users understand the relationships between datasets without needing to reverse engineer data lineage at the physical storage layer. Effectively, these constraints act as a foundational agreement between you and the engine, defining how data is related and potentially queried. Although they don't prevent the insertion of duplicate records, they help the system navigate your schema with more intent and greater speed. Refining your model is an iterative process that requires balancing strict schema design principles with the realities of analytical workflows. By focusing on surrogate key management, disciplined SCD implementations, and the strategic use of constraints for optimization hints, you build a robust environment for your data consumers. Each decision you make, whether to normalize or denormalize a particular dataset, should be driven by the specific latency requirements of the reports or dashboards being powered by that data. As you continue to work within this platform, remember that the goal is not to force a rigid structure upon the data, but to create a flexible framework that accounts for both history and current insight. Your ability to model effectively ensures that the Lakehouse remains an engine for discovery rather than becoming a bottleneck for your organization. Taking a thoughtful approach to these techniques will pay dividends as your complexity scales. I look forward to discussing how these models perform at scale in the following session. Welcome back. In this session, we investigate the mechanics of performance optimization and the diagnostic tools available within Databricks. To understand why a query performs poorly, you must first learn how to read the execution plan. When you prepend the explain keyword to any SQL statement in Databricks, the engine returns a logical and physical plan detailing how it intends to retrieve and process your data. This plan is not merely a theoretical exercise, but a breakdown of the specific operations, such as broadcast joins, shuffle hash joins, or sort merge joins, that the Spark engine will execute. By analyzing this output, you can identify expensive operations that consume excessive cluster resources or take disproportionate time to complete. Specifically, watch for signs of heavy shuffles, which occur when data needs to be moved across the network between nodes, as these are often the primary culprits behind high latency. If you see a Cartesian product in your plan, it indicates that your join conditions are likely missing or incorrectly defined, causing the engine to compare every row of one table against every row of another. Recognizing these structural inefficiencies in the plan is the first essential step toward writing more performant analytical queries. Beyond textual plans, the SQL Query Profile UI provides a visual representation of the execution lifecycle, which is invaluable for identifying bottlenecks like disk spilling and data skew. Disk spilling happens when the memory allocated to a given task is insufficient, forcing the engine to write intermediate data to local storage, which is orders of magnitude slower than in-memory processing. If you observe high spill metrics in the Profile UI, you should consider increasing the size of your SQL warehouse or optimizing the query logic to reduce memory footprint. Data skew, on the other hand, occurs when one partition holds significantly more data than others, causing a single task to take much longer while others sit idle. You can often detect skew by looking for uneven distribution of rows across tasks within a specific stage of the query. By addressing these imbalances, perhaps through salt values or better join keys, you allow the engine to distribute the workload more uniformly across the available compute nodes. This fine-grained visibility is what separates an effective data analyst from one who guesses why a report might be running slow. Caching behavior within Databricks is another critical factor that influences your query performance, though it is important to distinguish between the various types available. The disk cache, sometimes referred to as the local SSD cache, transparently stores data files from remote cloud storage onto the local disk of the worker nodes to speed up subsequent reads. The result cache, by contrast, stores the actual output of a specific SQL query, allowing the system to skip execution entirely if the exact same query is submitted again with the same underlying data state. While both are powerful, they serve different purposes and operate at different layers of the architectural stack. Relying on the result cache is excellent for performance, but it is limited by its sensitivity to changes in the underlying table data. Any modification to the delta table will invalidate the cached result. Therefore, you should design your workflows to leverage these caches consciously, rather than expecting them to magically solve architectural deficiencies in your data pipeline. Data skipping is a set of techniques designed to prevent the engine from scanning every single row in your dataset, and it represents the most effective way to reduce I/O costs. Partitioning is the most fundamental approach, where you organize data into a directory structure based on high cardinality columns, allowing the query engine to ignore irrelevant directories entirely based on your where clauses. To further enhance this, Databricks utilizes Bloom filters, which are probabilistic data structures that quickly tell the engine if a specific value is absent from a file, thus avoiding unnecessary file opens. For columns that are not suitable for partitioning, ZORDERing acts as a powerful index-like optimization by rearranging the data within files to cluster related information together. This process significantly increases the effectiveness of min-max statistics, ensuring that when the engine reads metadata about a file, it can accurately skip that file if the requested data range is not contained within it. When you combine Z-ordering with thoughtful partition design, you create a storage layer that is inherently optimized for the specific access patterns of your analytical workloads. See you in the next lecture. Welcome back to our discussion on data governance and security. In this chapter, we will unpack how Unity Catalog revolutionizes the way you manage data assets across your entire Databricks environment. To truly understand Unity Catalog, we must first look at the transition from the legacy Hive Metastore to this modern, unified governance model. Historically, the Hive Metastore operated at a workspace level, creating silos that made centralized security and data sharing cumbersome and prone to inconsistency. Unity Catalog removes these limitations by decoupling governance from individual workspaces and elevating it to the account level. It introduces a three-level namespace structure, which is defined as catalog, schema, and table or view. This hierarchy provides a systematic way to organize assets, where a catalog acts as the top-level container, a schema acts as a logical grouping of assets within that catalog, and a table or view represents the actual data structure. By enforcing this structure, Databricks ensures that every object in your environment has a unique, fully qualified identifier, which simplifies cross-workspace access and data discovery significantly. The foundation of this architecture is the metastore itself, which is the root of the hierarchy. When you configure a metastore, you are essentially establishing the central authority for all metadata and access control policies within your Databricks account. While a metastore is created at the account level, it must be explicitly assigned to one or more Databricks workspaces to become operational. This assignment process is precisely what allows you to maintain centralized governance over diverse compute resources without duplicating your efforts or policy definitions. When you leverage Unity Catalog, you get a single pane of glass for all your data, regardless of which workspace is currently accessing it. This architectural shift means that if you grant access to a user at the catalog level, that permission is respected consistently across every workspace linked to that metastore. It creates a robust, secure perimeter that was simply impossible to maintain reliably under the old, fragmented metadata approach. One of the most important concepts to grasp is the management of storage locations, specifically the distinction between managed and external tables. In Unity Catalog, a managed table stores both the data and the metadata within a location that Databricks manages on your behalf. When you drop a managed table, the underlying files are automatically deleted, which simplifies your data lifecycle management and helps keep cloud storage clean. Conversely, external tables allow you to maintain control over the underlying data files in your own cloud storage bucket, while Unity Catalog merely manages the metadata. This is particularly useful when you need to retain data for regulatory reasons, or when the data is being produced and consumed by systems outside of Databricks. Understanding when to use managed versus external locations is a fundamental skill for any data analyst, as it balances the convenience of automated management with the necessity of architectural flexibility. The benefits of this centralized governance model extend far beyond just security access. Because all assets exist within a unified namespace, Databricks can automatically capture lineage information across your entire data landscape. You can trace how data moves from raw ingestion sources through your transformation pipelines and into final analytical tables or dashboards. This level of transparency is essential for compliance auditing and for building trust among data consumers who need to understand the provenance of their metrics. Furthermore, by standardizing the way objects are defined and accessed through SQL, Unity Catalog ensures that your analytical queries remain portable. Whether you are running complex joins or simple aggregations, the logic you write remains consistent because the underlying object references follow the same hierarchical standard. This unified governance is what allows large organizations to scale their data operations without sacrificing control or visibility over their critical information assets. See you in the next lecture. Welcome back. We are now diving into the practical mechanics of securing your data assets within Unity Catalog. In this session, we will examine how to implement granular access control patterns to ensure your data remains both accessible to those who need it and protected from those who do not. Effective governance in a modern data platform relies heavily on the principle of least privilege, which dictates that any identity, whether a human user or a programmatic entity, should be granted only the minimum permissions necessary to perform its functions. When operating within the Unity Catalog hierarchy, permissions are applied at different levels, ranging from the metastore down to individual catalogs, schemas, tables, and even specific functions. The grant statement serves as the primary mechanism for assigning rights, while revoke is used to withdraw them, allowing administrators to maintain a precise control plane. It is important to remember that these permissions are not merely additive, but exist within a structured hierarchy where parent objects often influence the effective permissions of their children. By thoughtfully architecting your permission grants, you reduce the risk of accidental data exposure while maintaining a predictable security posture across your multi-tenant environment. Understanding the ownership model is critical because the owner of an object possesses full control, including the ability to issue grant statements to other users or groups. When a user creates an object, such as a table or a schema, they naturally become its owner. But you should consider the implications of this in an enterprise setting, where individual departures could lead to orphaned resources. Best practice suggests assigning ownership of critical production assets to a service principal or a dedicated administrative group rather than an individual account. This approach ensures that your security configuration remains stable and auditable regardless of staff turnover within your organization. Furthermore, because Unity Catalog treats these ownership attributes as metadata, they are easily transferable via SQL commands, which allows you to maintain clean administrative boundaries as your data ecosystem scales. In any production-grade system, managing permissions for individual users is an unsustainable pattern that leads to configuration drift and security gaps. Instead, you should focus your efforts on managing permissions for groups and service principals, which act as stable abstractions for your organizational roles. When you grant read access to a schema for the data engineers group, you ensure that every member of that group automatically inherits access, eliminating the manual overhead associated with individual user maintenance. Service principals are equally vital, as they provide an identity for automated tasks, such as ETL pipelines or reporting services, without requiring shared credentials or interactive logins. By requiring that all automated workflows authenticate via these service principals, you gain a clear, traceable history of data access that integrates seamlessly with your compliance monitoring systems. The concept of inheritance plays a significant role in how effective permissions are calculated throughout your Lakehouse hierarchy. When you issue a grant at the catalog level, those permissions propagate downwards through the schemas and tables contained within, creating a cascading effect that simplifies administrative policy enforcement. While this inheritance model is powerful for broad access requirements, you must be cautious about overgranting at higher levels, as it can inadvertently expose sensitive tables deeper in the hierarchy. If you encounter a situation where broad access is appropriate for a catalog, but a specific table requires stricter control, you can apply more restrictive permissions to override or supplement the inherited rights. This granular capability allows you to balance the need for simplified bulk management with the security requirements of highly sensitive datasets. Finally, you should cultivate a habit of auditing your access control lists regularly to ensure that no permissions have drifted from your intended security architecture. Because Unity Catalog keeps a central log of all authorization changes, you can verify exactly who granted which permission and when it was modified. In a multi-tenant environment, this visibility is non-negotiable, as it provides the evidence needed to satisfy internal governance audits and external compliance mandates. Rather than manually inspecting individual tables, lean on system tables and platform auditing tools to provide summaries of effective permissions across your workspace. By treating security as code, you can version control your access policies, ensuring that your data platform remains secure, consistent, and fully aligned with your organizational compliance requirements. I trust this provides a solid foundation for managing your access controls effectively. See you in the next session to build on these concepts. Welcome back. Today, we are tackling the implementation of dynamic row-level security to ensure your data access patterns remain both secure and highly granular. In an enterprise environment, the requirement to restrict data access based on a user's department or identity often arises as a non-negotiable security mandate. Traditionally, one might be tempted to create separate physical tables for different segments of users, but this approach introduces significant maintenance overhead and risks data fragmentation. Instead, Databricks provides a much more elegant solution through the Unity Catalog, which allows us to define security predicates directly on existing tables. By implementing dynamic row-level security, we can apply a filter that automatically evaluates the context of the current requester, ensuring that the result set of a query is restricted to only what that specific user is permitted to see. This abstraction means that your underlying data remains in a single, unified table, significantly simplifying your schema management while simultaneously enforcing strict compliance boundaries. The cornerstone of this pattern is the creation of a user-defined function, or UDF, that acts as a gatekeeper for your data rows. Within the Unity Catalog ecosystem, we can leverage specific built-in functions, most notably is account group member, to determine the identity or the organizational context of the user running a query. When you define a row filter, Databricks invokes this function for every row retrieval operation, evaluating the Boolean expression returned by your logic. If the function returns true for a given row, the data is visible. If it returns false, the record is silently excluded from the query results. This happens mid-execution, meaning that end users, such as those working within the SQL editor, remain completely unaware that the underlying dataset is being filtered behind their backs. It provides a seamless experience for the consumer while maintaining a robust security posture for the data owner. Consider a scenario where you have a central sales table that contains records from multiple regional departments, such as North America, Europe, and Asia. Rather than splitting this into three disparate tables, you can create a function that takes a department identifier and checks it against the authenticated user's group membership. You then attach this policy to your table using the alter table statement, specifying that the filter applies to the column containing the regional identifier. If a user belongs to the Sales in A group, the is account group member function will confirm their membership, and the filter will allow access only to rows where the region code matches that group's assigned values. Consequently, when an analyst queries the entire table, the security logic dynamically subsets the returned rows without requiring the analyst to append manual where predicates or have knowledge of the row-level constraints. Testing and auditing are critical components of maintaining this security model, especially when multiple personas are involved in a reporting ecosystem. Once your row filter is in place, you should verify its effectiveness by impersonating different user roles within your SQL editor environment. This allows you to confirm that a user from the Sales Europe group cannot see, aggregate, or accidentally expose data belonging to Sales Asia. Beyond simple verification, Unity Catalog keeps detailed audit logs regarding these access patterns, which are vital for meeting regulatory mandates like GDPR or HIPAA. By inspecting the query profile and audit logs, administrators can ensure that the security predicate is being applied as expected and that no unintended data leakage is occurring. Having a transparent and repeatable auditing process for these policies is what distinguishes a mature data governance strategy from a merely functional one. Always remember that these filters are reactive and context-aware, which provides the flexibility needed for changing organizational structures without refactoring your SQL models. Because the logic is tethered to the table definition and the user's identity group, you can update a user's access simply by changing their membership in the underlying identity provider. There is no need to drop and recreate tables, modify complex view hierarchies, or update every BI report downstream. This centralized approach to governance ensures that security policies are consistent across the entire platform, regardless of whether a user is connecting via the SQL editor, a dashboard, or an external BI tool. By mastering this dynamic capability, you move away from static, brittle permissions and into a future-proof model that scales alongside your data architecture. Look forward to discussing our next topic in the following session. Welcome back to our exploration of Unity Catalog, where we will now shift our focus toward protecting sensitive information through column-level masking. This lesson covers how to apply masking policies to specific columns to ensure that personally identifiable information remains secure while maintaining analytical utility. Data governance is not just a regulatory obligation. It is a fundamental architecture principle in the Databricks Lakehouse. When we talk about personally identifiable information, we are referring to any data that could potentially identify a specific individual. In a modern data environment, we cannot simply rely on broad access controls, as different personas within the same organization often require varying levels of granularity. By implementing column-level masking, we effectively redact or transform sensitive data at query time, ensuring that the underlying storage remains intact while the presentation to the end user is restricted. This approach allows a data analyst to query a table containing email addresses or social security numbers without ever actually seeing the raw, unmasked values, unless they possess the specific permissions to do so. It is an elegant solution because it decouples physical data storage from logical data access, ensuring that compliance with regulations like GDPR or HIPAA does not compromise the ability to perform aggregate analysis on non-sensitive aspects of the same datasets. To implement this, we typically leverage SQL functions associated with Unity Catalog's dynamic masking capabilities. These functions allow us to define logic that executes every time a user selects data from a masked column. The most robust way to manage this is by utilizing conditional logic, specifically case statements, within our masking functions. Imagine you have a customer table that contains a phone number column. A data analyst might need to perform a count of customers by region, which only requires the area code, whereas a customer support representative might need the entire number to resolve a ticket. By wrapping the masking logic in a case statement that checks the current user's role or identity, we can return the full string for authorized personnel while returning an obfuscated hash or a redacted string like XXX, XXX, XXX for everyone else. This conditional security pattern is powerful because it allows us to define a single security policy that gracefully handles multiple security domains, effectively reducing the administrative overhead associated with maintaining separate views for different user cohorts. The beauty of this architecture lies in its ability to support differential privacy and selective visibility without creating dozens of redundant views. When a query is submitted to the SQL warehouse, Unity Catalog evaluates the policy applied to the target column and modifies the query result set before it ever reaches the user's interface. Because this happens on the server side, the obfuscation is consistent regardless of whether the user is querying through a notebook, a SQL dashboard, or an external BI tool connected via Partner Connect. If you need to adhere to compliance standards, you avoid the common trap of extracting multiple filtered copies of the same dataset. Instead, you maintain one version of the truth, applying a mask that preserves the statistical distribution of the data if necessary, or simply suppressing it entirely. This method is essentially a form of functional composition where the security requirement is injected into the read path of the data, keeping your analytics pipelines clean and your PII strictly governed. When architecting these policies, I recommend evaluating the impact of the masking logic on the performance of your downstream operations. While SQL masking functions are highly optimized, constant evaluation of role-based logic in a complex join operation can occasionally introduce overhead if not carefully considered. Always aim for the simplest form of masking that meets your compliance requirement, such as full redaction or simple fixed character masking, before moving to more intensive procedures like deterministic hashing. Deterministic hashing is often a great middle ground, as it allows users to perform join operations or count unique identifiers across tables without actually knowing the underlying clear text value. By combining these strategies, you maintain the utility of your lakehouse for legitimate business insights while strictly enforcing the perimeter required to protect the privacy of your users. Until next time. Welcome back. Today we examine the practical aspects of tracking data movement and understanding metadata within the Databricks ecosystem. In any robust data environment, knowing exactly where your data originates and how it transforms is not merely a luxury but a fundamental requirement for maintaining trust. When we talk about data lineage, we are essentially discussing the ability to map the journey of a data asset from its initial ingestion point through every transformation layer until it reaches the final consumption layer. Within the Databricks environment, specifically when utilizing Unity Catalog, this capability is front and center via the Lineage UI. This graphical interface provides an automated visualization of relationships between tables, views, and external assets, which significantly simplifies the developer's cognitive load when performing root cause analysis. Instead of manually parsing through hundreds of lines of complex SQL scripts to trace a column's origin, you rely on the system-generated metadata that captures these dependencies natively. This is particularly useful in the Medallion architecture, where data flows systematically from bronze to silver and finally to gold layers, allowing you to see the propagation of logic across these stages clearly. The primary utility of Lineage becomes apparent when you need to enact schema changes or perform maintenance on a legacy pipeline. By identifying upstream dependencies, you can assess the potential blast radius of a code modification before it is pushed into production, thereby preventing unintended downstream outages. For example, if you intend to rename a column in a bronze table, the Lineage UI allows you to inspect which silver-level transformations or gold-level aggregates are consuming that specific attribute. This proactive approach to data management transforms the way we approach schema evolution, moving us away from a trial-and-error cycle toward a more deterministic engineering workflow. Understanding these connections is foundational for any data analyst who carries the duty of ensuring the accuracy and reliability of the data products provided to stakeholders. It acts as an automated documentation layer that is always in sync with reality, as it is captured by the underlying platform engine rather than maintained manually by human operators. The graphical interface provides an excellent heuristic view of your architecture. There are instances where programmatic access to deep metadata is required for comprehensive auditing. This is where the information schema becomes an indispensable part of your toolkit, as it provides a standardized, SQL-based interface to query your account's metadata. By querying the information schema, you can retrieve granular details about table definitions, configuration parameters, and even historical audit logs for various objects within the Unity catalog hierarchy. This allows you to build custom tracking solutions, such as reporting on which users have accessed sensitive tables or verifying that specific transformation jobs are executing within expected timeframes. You can think of the information schema as the introspection layer of the Databricks environment, enabling you to treat metadata as data. This is a powerful paradigm because it allows us to apply the same SQL expertise we use for business reporting to the administrative task of managing the health and provenance of our data assets. Tracking provenance across the various stages of the Medallion architecture relies on the consistent application of Unity catalog features to all assets regardless of their layer. When tables are registered within the catalog, Databricks automatically captures internal transformations, allowing you to see lineage even at the column level for complex operations. This level of transparency is essential for debugging scenarios where an aggregate value in a final report differs from the expected output, as you can quickly jump back through the chain of lineage to the specific source table that might contain anomalous data. As an analyst, you are likely to encounter scenarios where you must certify that the data feeding a dashboard satisfies compliance or quality standards before stakeholders make executive decisions. By using these lineage tools and metadata queries, you provide an evidence-based trail for every data point, which is exactly what a well-architected data platform promises to deliver. Maintaining such visibility ensures that you are always in control of your data ecosystem, even as it grows in size and complexity. I will see you in our next session. Welcome back. In this lesson, we will focus on the practical implementation of auditing and compliance monitoring within the Databricks ecosystem. When we talk about enterprise data platforms, security is rarely an afterthought. It is, or at least it should be, a foundational design principle. In the context of Databricks, auditing and compliance monitoring allow us to maintain a transparent record of all interactions within our unified analytics platform. We rely on system tables, which act as the authoritative source of truth for all telemetry, configuration changes, and access requests. These tables, specifically those housed under the system catalog, capture the who, what, where, and when of every action performed by users or service principals. As a data analyst, understanding how to query these tables provides you with the visibility required to ensure that your organization remains compliant with internal policies and external regulations. Accessing these logs is not merely a technical exercise, but a necessary step in verifying that our governance posture remains intact. The primary interface for this visibility is found within the system schema, where logs like access, audit, and query history are stored. By querying the system.access.audit table, you can reconstruct the sequence of events leading to a particular state. This is particularly useful when you need to inspect the provenance of a specific data object or verify that sensitive data access follows the principle of least privilege. For example, if you detect an anomaly in a downstream report, you can correlate that data movement with specific user credentials stored in the audit logs. Furthermore, the query history system table allows you to audit the SQL statements themselves. This transparency ensures that you can identify users who might be performing unexpected or unauthorized data exfiltration attempts through aggressive bulk query patterns. Such depth of information is what separates a managed lakehouse from an unorganized data repository. Monitoring user activity and query history is not just about catching malicious actors. It is fundamentally about performance auditing and operational intelligence. By analyzing query history, you can identify inefficient, long-running jobs that might interfere with critical production workflows. When we inspect the SQL query profile, we aren't just looking for errors, but also for opportunities to optimize execution plans. You might notice that a particular user is constantly performing full table scans on large partition tables, which would suggest a need for better user training or index optimization. By integrating these history logs into your routine monitoring, you enforce a culture of accountability where every query has a traceable performance cost. This systematic approach to query auditing allows the data team to maintain high availability while minimizing compute wastage within SQL warehouses. Beyond manual inspection, we must talk about proactive security monitoring through alerts. Relying on reactive auditing is rarely sufficient in an environment that processes terabytes of information in real time. We can implement alert mechanisms that trigger whenever a user attempts to access a restricted schema or modifies a critical governance configuration, such as a change to a table access control list. When you configure these alerts, you are essentially setting up tripwires that notify the appropriate security stakeholders the moment an unauthorized access attempt occurs. In the context of Unity Catalog, these configurations are managed as metadata, and any alteration to these policies should be treated as a sensitive event. Consistent monitoring of these governance configurations ensures that the security perimeter is not circumvented by configuration drift over time. Maintaining compliance involves a continuous loop of data access pattern analysis and policy tuning. Because the Databricks Lakehouse centralizes data storage and compute, you can perform these audits across both metadata and actual data files consistently. You can monitor whether your data access patterns align with the sensitivity levels designated in your catalog, such as ensuring that PII tag columns are only accessed through specific, authorized application rules. If you identify a pattern where unauthorized service accounts are querying sensitive tables, you have the historical data to support immediate revocation of permissions. This level of rigor is exactly what examiners look for during the certification process, as it demonstrates an understanding of the full data lifecycle. Compliance is never a static checkbox exercise. It is the constant validation that your data governance model matches the reality of usage in your workspace. Understanding these monitoring capabilities is essential for your upcoming certification. I will see you in the next lesson. Welcome back. We are now moving into the administrative side of the Databricks SQL Workspace, where we focus on managing your SQL assets effectively. In this chapter, we will explore how to organize your SQL queries, dashboards, and alerts, ensuring that your workspace remains maintainable and secure. You will learn how to implement proper folder structures for collaboration, manage permissions, and track dependencies between various objects. We will also cover the practicalities of versioning and moving assets across different environments in your enterprise. By the end of this chapter, you will possess the skills necessary to keep a production-grade Databricks environment clean, orderly, and highly performant for your entire data team. The Databricks SQL Workspace offers more than just a place to write queries. It acts as a central repository for your analytical logic. When working in teams, organization is the first line of defense against technical debt. You should think of your workspace folders much like a file system in a sophisticated software project. By grouping related queries, dashboards, and alerts into shared folders, you establish a clear hierarchy that reflects your business domains or project boundaries. This structure is not merely aesthetic, it is structural, as ownership and access permissions are frequently inherited from these directory-level configurations. When you define permissions at the folder level, you avoid the manual overhead of managing individual objects, which is a common source of security misconfigurations in larger organizations. Managing collaboration through permissions is a nuanced task that requires a least privilege mindset. Databricks provides distinct roles such as can view, can run, can edit, and can manage. You must carefully consider who truly needs the ability to modify the definition of a query compared to those who only need to consume its output via a dashboard. Collaboration often suffers when permissions are too restrictive, yet security is compromised when they are too permissive. Using shared folders allows you to delegate administrative control to lead analysts while ensuring that junior members have enough access to perform their operational duties safely. Always review these settings periodically to ensure that as your team changes, your internal security posture remains aligned with your organizational policies. Version control for SQL assets is another critical area that separates professional data engineering teams from those that rely on copy-paste methods. While Databricks provides a basic history for queries, Professional workflows usually involve integrating with Git or using the workspace as a staging area before moving code to a source-controlled repository. You need to understand that a dashboard is essentially a metadata wrapper around one or more underlying queries. If you change a column name in a SQL query, any dashboard or alert consuming that data will likely fail if the logic is not updated in tandem. This dependency creates a brittle ecosystem if you treat these assets as isolated entities. You must always map these relationships when performing refactoring or folder migrations. Movement of assets between workspaces also requires careful attention to the dependencies hidden within your SQL code. When you export or import assets, you are essentially serializing the object definitions, but you are not necessarily carrying over the underlying data warehouse context or the specific connection strings. Alerts are particularly sensitive to these migrations. An alert is bound to a result set, which is in turn bound to a specific query ID. If you move a query to a new folder or a different workspace, ensure that the downstream alerts are correctly relinked and validated. Failure to account for these dependency chains often leads to silent failures, where updates are no longer triggered because the link between the data and the notification mechanism has been severed during the export process. Beyond simple organizational hygiene, there is a technical necessity to treat your SQL workspace as a production system. This implies that documentation, naming conventions, and asset ownership are components of your metadata strategy. When you build complex dashboards that rely on multiple materialized views or underlying tables, document those dependencies within the asset metadata or a supporting internal wiki. This practice pays off when you need to perform maintenance or upgrade your data architecture, as it prevents the accidental deletion of foundational objects. As you grow comfortable with the Databricks SQL workspace, you will find that these seemingly administrative tasks are actually the glue that holds your data platform together. Mastering these tools ensures that your analytics output is consistent, reliable, and prepared for enterprise-level demands. See you in the next lesson. Welcome back. In this lesson, we explore how to bridge the gap between your governed Databricks environment and the external business intelligence tools that your organization relies upon daily. When we talk about external BI integration, we are essentially discussing the plumbing that allows tools like Power BI, Tableau, or even custom Python applications to read data residing in your lakehouse. Databricks provides a feature called Partner Connect that simplifies this integration significantly by automating the creation of connection profiles for various BI vendors. Instead of manually navigating through driver versions or complex authentication strings, Partner Connect generates a pre-configured file that you can import directly into your BI tool. This approach not only saves time, but also ensures that the connection is established using the recommended security protocols and standard driver configurations. Behind the scenes, these connections still rely on the robust foundation of JDBC and ODBC standards, which remain the industry benchmark for structured data exchange. Understanding that your BI tool is essentially acting as a SQL client is critical for troubleshooting connectivity or performance issues. When you initiate a query from an external dashboard, it travels over the network, is processed by the SQL warehouse, and the result set is returned through these standardized drivers. Security is a primary concern when connecting external systems, and this is where personal access tokens, or PATs, become essential for authentication. A PAT acts as a secure, long-lived credential that grants your BI tool permission to impersonate your user identity when communicating with the Databricks API. To generate one, you navigate to your user settings, create a token, and ensure you store it securely, as it effectively functions like a password. When configuring a connection string, you will often find that you need to provide the hostname of your Databricks workspace, the HTTP path of your SQL warehouse, and your authentication credentials. The HTTP path is particularly important because it tells the driver exactly which compute resource should handle the incoming request. If you're using a tool that does not officially support Partner Connect, you will be responsible for manually downloading the correct ODBC or JDBC driver from Databricks. It is prudent to keep these drivers updated, as Databricks frequently releases performance improvements and security patches for their connectivity stack. Once a connection is established, the efficiency of your BI tool depends heavily on how you leverage SQL warehouses. We must view the SQL warehouse not just as an execution engine, but as a compute resource that can be scaled independently to match the demands of your reporting workload. For instance, when using the specialized Power BI connector, you benefit from optimized data loading techniques that are specifically tailored for the Databricks platform. These connectors understand how to handle metadata requests and schema discovery far better than generic ODBC drivers, leading to a snappier user experience when browsing tables. Furthermore, you should always aim to push as much processing as possible to the SQL warehouse, rather than pulling massive amounts of raw data into your BI tool's local memory. By utilizing efficient filters and aggregation at the source, you ensure that only the necessary result set is transferred over the wire. This not only reduces network latency, but also prevents common bottlenecks that occur when a local client attempts to process large data sets that the Lakehouse is perfectly capable of handling in seconds. In an enterprise setting, managing these integrations involves considerations beyond simple connectivity, such as how you share these data sources with other analysts. When you connect a BI tool to a SQL warehouse, you are essentially creating a virtual bridge, and it is your responsibility to ensure that the Unity Catalog permissions remain the ultimate source of truth. If a user is not authorized to see specific tables in the catalog, they will not see those tables through the BI connector either, provided your environment is correctly configured. This consistency is one of the most powerful features of the current Lakehouse architecture, as it centralizes security policy enforcement across all access methods. As you design your dashboards, keep in mind that the throughput of your connection is often dependent on the size of the SQL warehouse you choose to expose. A serverless SQL warehouse, for example, offers rapid startup times and can automatically handle concurrency, which is an ideal choice for dashboards that are frequently refreshed by multiple users across your organization. Always monitor the query history logs to see if your external queries are experiencing serialization delays or high wait times for compute resources to spin up. See you in the next lecture. Welcome back to our journey through the Databricks SQL environment. Today, we will explore the foundational principles of effective data visualization within the workspace. Data visualization is rarely about making charts look aesthetically pleasing. It is primarily about reducing the cognitive load required to understand complex datasets. When you work with raw query results in Databricks, you are essentially looking at a multi-dimensional matrix of information that is difficult for the human brain to process in its tabular form. By selecting the correct visualization type, you convert these abstract rows and columns into distinct patterns, trends, or outliers. A bar chart, for instance, excels at comparing categorical values where the length of the bar provides an intuitive sense of magnitude. If your goal is to show how a metric changes across a granular timeline, a time series plot is the industry standard because it leverages our innate sense of continuity and progression. However, common pitfalls include using pie charts for datasets with many categories, which makes it nearly impossible for the viewer to accurately compare the sizes of individual slices. Being effective in your role means choosing the visualization that matches the data distribution and the specific business question you intend to answer. Within the Databricks SQL Workspace, the configuration panel offers extensive control over your rendered output, and mastering these settings is key to professional reporting. You should consistently look at the axis formatting options where you can define scales, labels, and ranges to prevent misleading representations. For example, starting a bar chart axis at a value other than 0 can artificially inflate the perceived differences between values, which is a dangerous practice in business reporting. Beyond numerical formatting, the choice of color palettes plays a critical role in accessibility and thematic consistency. You should strive to use high-contrast color sets when displaying multiple data series to ensure distinguishability while adhering to organizational standards if they exist. Databricks also allows you to configure tooltips and data point labels, which provide necessary context without cluttering the initial view. By refining these configuration settings, you ensure that the chart remains readable even as your underlying query results evolve over time. While bar and time series plots represent the majority of daily dashboards, specialized visualizations like scatter plots and maps are essential for specific analytical tasks. A scatter plot should be your go-to visualization when you need to identify relationships or correlations between two numerical variables across a large population of data points. For instance, plotting customer lifetime value against the frequency of purchases often reveals clusters that might define your target audience segments. Conversely, maps are reserved for scenarios where geographical distribution is the primary driver of insight. though they require your data to contain clear spatial identifiers like country codes or specific coordinate points. In each of these cases, the transformation from raw query results to a compelling visual narrative must be seamless and repeatable. The goal is to provide a dashboard experience where the stakeholders do not need to query the underlying delta tables manually because the visual itself contains the answer to their most common questions. Effectiveness in visualization also hinges on understanding the limitation of the tool at hand and the nature of the data you are feeding into it. Databricks SQL handles aggregated data efficiently, but you must ensure your underlying SQL queries perform the necessary transformations before the visualization layer consumes them. If you attempt to visualize millions of rows without proper aggregation using SQL functions, the browser will struggle to render the chart, resulting in a poor user experience. Always perform heavy lifting, like filtering, grouping, and ordering within your SQL editor before configuring the visualization settings to ensure your dashboard remains performant. By mastering the distinction between exploratory data analysis, where you might use quick scatter plots, and polished dashboarding for stakeholders, you align your technical implementation with business value. Remember that the best visualization is one that requires the least amount of explanation for the observer to grasp the core takeaway. I will see you in the next lecture. Hello, welcome back. In this chapter, we will explore the techniques required to consolidate isolated visualizations into cohesive, interactive dashboards designed for business users. Building a dashboard is rarely about merely placing charts on a canvas. It is an exercise in data storytelling and user experience design. When you transition from a raw SQL query to a dashboard, your primary objective shifts from answering a single technical question to providing a decision-making tool for non-technical stakeholders. Within the Databricks SQL environment, the dashboard serves as the interface between the complex, high-performance Delta Lake architecture and the end user who needs rapid insights. To succeed in this, you must treat your dashboard as an application that requires careful layout planning, logical grouping of metrics, and a clean interface that avoids overwhelming the viewer with too much cognitive load. One of the most powerful features you have at your disposal is the use of parameters within your underlying queries. By substituting hard-coded filter values with parameters, you allow the dashboard to dynamically adapt to different contexts without requiring the user to touch a single line of SQL code. For example, if you are building a regional sales report, instead of writing separate queries for each state, you define a parameter for the region. This turns your dashboard into a self-service asset where stakeholders can slice data by date, category, or geography at their leisure. Implementing these parameters correctly is fundamental for passing the associate certification, as it showcases an understanding of how to bridge the gap between technical data engineering and executive reporting needs. Effective dashboard layout is just as important as the data quality behind the scenes, so you should prioritize clarity when arranging your visualizations. Databricks allows you to incorporate text boxes to provide context, label your sections, and give clear instructions to stakeholders on how they should interpret the displayed metrics. A common mistake is to clutter the dashboard with too many individual charts that fight for the user's attention. Instead, follow a logical flow where you start with high-level key performance indicators, often displayed as large, bold counter figures, followed by trends or distribution charts that explore the why behind the numbers. When you add filters and widgets, always ensure they are placed in obvious locations, typically at the top or the left-hand sidebar, to maintain a consistent navigation pattern. Consistency leads to better adoption, so I suggest establishing a standard for your dashboard designs, especially when working in a team environment. Use consistent color schemes for your charts throughout the dashboard, as this helps the audience quickly recognize categories without constantly rereading legends. Beyond the visual appeal, you must ensure that your dashboard queries are optimized to handle frequent refreshes. Since multiple users might be interacting with your parameters simultaneously, the underlying SQL warehouses must be configured appropriately to prevent latency. By understanding the limitations of your compute resources, you balance the need for real-time interactivity with the reality of infrastructure costs, which is a hallmark of a mature data professional. Remember that the ultimate goal is to enable stakeholders to explore data without human intervention. If a stakeholder has to come back to you every time they need a slightly different view of a report, the dashboard isn't doing its job. Think of yourself as an enabler of truth rather than a gatekeeper. By utilizing parameters effectively, you empower your users to find their own answers, which frees up your time for more complex analytical projects. Take the time to document your parameters within the dashboard's text blocks so that any user, regardless of their background, can feel confident in manipulating the filters to derive the insights they require. See you in the next lecture. Welcome back. In this session, we will examine how Databricks widgets transform static reports into interactive, self-service analytical applications. When we consider the necessity of data democratization, we often encounter a tension between the rigid structure of predefined queries and the spontaneous curiosity of business users. Widgets offer a mechanism to bridge this divide by introducing runtime parameters directly into the Databricks SQL environment. By substituting hard-coded constants in our SQL statements with dynamic references, we allow users to manipulate the context of an analysis without needing to touch the underlying codebase. The syntax for this is remarkably straightforward, involving a specific double brace notation that instructs the execution engine to look for a corresponding UI element. When you define a variable, such as a date range or a product category, you are essentially establishing a contract between the dashboard interface and the data transformation logic. This separation of concerns is a standard practice in software engineering, and here it serves the practical purpose of keeping our queries reusable across different dimensions of inquiry. There are 4 primary widget types we utilize to capture user input, each serving a distinct interaction pattern. The text widget provides the most flexibility, allowing users to type free-form strings, which is useful for identifiers or specific filters that cannot be categorized in advance. The drop-down widget, conversely, is the bedrock of constrained entry, preventing invalid data submissions while ensuring that users select from a curated list of available dimensions. For temporal analyses, a common requirement in our field, the date widget provides a localized, user-friendly calendar picker, removing the ambiguity associated with different date string formats. Finally, the numeric widget ensures that inputs conform to numerical constraints, which is particularly beneficial when managing thresholds, financial limits, or sample sizes. Configuring these widgets requires an understanding of the default values and label definitions that must be explicitly declared within the configuration panel to ensure a predictable initial state for whoever opens the dashboard. The true power of these interactive elements reveals itself when we pass these values into SQL queries using parameterized syntax. The Databricks environment intercepts these parameters, replacing the placeholders in your SQL code with the current value selected by the user before the statement is sent to the warehouse for execution. This is not merely string substitution, which would leave us vulnerable to injection flaws, but a structured parameter passing mechanism that maintains type safety. When you write a query, you signify a variable by enclosing its label in double curly braces, such as viewing sales, where the region equals the parameter selected in the interface. This architectural decision shifts the primary responsibility of filtering from the query author to the data consumer, effectively turning a single, well-optimized query into a flexible tool that can yield hundreds of unique insights. An optimized dashboard leverages this by ensuring that the underlying query remains efficient regardless of the specific parameters chosen by the user. Managing complex analytical requirements often necessitates what we call cascading parameters, where the content of one widget is dependent on the selection of another. Imagine a scenario where a user selects a specific country. It would be logically consistent for a second widget, perhaps representing a regional office, to only display options valid for that country. Implementing this requires a slightly more nuanced approach to how widgets are configured in the Databricks SQL Workspace. You define these relationships by ensuring that the query populating the dependent dropdown uses the value of the parent widget as an input variable itself. When the parent widget state changes, a re-execution of the dependent query is triggered, which dynamically updates the available selections based on the new context. This cascading logic prevents an exhaustive search across unrelated data points and significantly cleans up the user experience by keeping the interface focused on relevant, valid choices. Enabling self-service filtering is fundamentally about reducing the feedback loop between a business question and the delivery of an answer. By providing granular data drilling capabilities through these interactive widgets, You allow stakeholders to traverse the data hierarchy at their own pace. A dashboard might begin at an executive level, showing total revenue, but with the inclusion of widgets. The same page can be used by an operations manager to inspect daily throughput by facility. This level of granularity must be supported by performance SQL, as the constant re-execution of queries necessitates that your data models and underlying tables are properly indexed and partitioned. We strive for a balance where the dashboard remains responsive while offering the depth required by diverse user personas within the organization. By treating these interactive components as part of a coherent design system, we ensure that the democratization of data remains both secure and performant. See you in our next exploration of data operationalization. Welcome back. Today, we are going to explore how to transition from passive data observation to active monitoring through the configuration of automated alerts. In the context of a Databricks Lakehouse, the SQL alert functionality serves as a vital bridge between raw data state changes and human intervention. An alert is essentially a scheduled process that periodically executes a specific SQL query, evaluates the resulting data against defined threshold conditions, and triggers notifications if those conditions are met. This mechanism is not designed for real-time alerting in the sense of sub-second streaming responses, but rather for operational awareness regarding business KPIs or data quality metrics. When you define an alert, you are binding a query result, typically a scalar value or a count, to a logical trigger that monitors whether data has deviated from an expected baseline. This is especially useful for tracking patterns such as unusually high transaction volumes, a sudden drop in null counts within a critical column, or performance metrics that breach defined service level agreements. The foundation of any alert is the underlying query, which must return a single value or a result set that the system can interpret as a truth condition. You must ensure that your query is idempotent and efficient, as it will run at specific intervals against your SQL warehouse. When configuring the alert, the threshold logic is applied to the first record or a designated column in your query result. If the query detects a violation, for example, if a count of failed pipeline records exceeds 0, the alert transitions to a triggered state. It is vital to consider the refresh schedule of the underlying SQL warehouse, as the alert scheduler relies on the availability of this compute resource to evaluate the query. If the warehouse is paused or underpowered, the evaluation request may queue or fail, which disrupts the operational continuity of your monitoring solution. Once a condition is met, Databricks provides a flexible notification infrastructure to ensure the right stakeholders receive the information. Notification destinations include native support for email, alongside integrations for collaboration platforms like Slack and incident management systems like PagerDuty. These destinations are managed centrally and linked to your alert configurations, allowing you to route alerts to different teams based on the severity or the persona associated with the data. You can customize the alert notification templates to include context-rich information, such as the specific value that triggered the alert, a direct link to the query, or a custom message to guide the user in their investigation. This personalization reduces the time between notification and mitigation because the recipient immediately understands the scope of the potential incident without needing to open the platform initially. Managing the frequency of these notifications is a critical aspect of operational hygiene, specifically through the use of re-trigger intervals. Without proper interval management, a query that remains in a breached state could generate a deafening volume of notifications every time the alert runs. The retrigger interval defines the minimum duration that must pass before the system sends another notification for the same alert condition. This is a simple but effective mechanism to prevent alert fatigue, which is a common failure mode in mature data organizations. By carefully tuning these intervals, you balance the need for immediate visibility with the requirement to stop unnecessary noise, ensuring that when a notification arrives, it represents an actionable event rather than just redundant information. From a data quality perspective, adopting alerts represents a proactive shift in how you maintain the Medallion architecture. Rather than waiting for a downstream report to show broken data, you can build alerts directly on your bronze or silver tables to verify integrity constraints, such as ensuring unique primary keys or checking that mandatory fields are populated. When combined with operational KPIs, this makes the Lakehouse a self-monitoring system that serves both technical data engineers and business analysts. Security and governance should remain at the forefront, as the alert itself runs under the credentials of the user who owns or configured it, or within the context of established service principles. As you implement these configurations, always audit who has the capability to create and modify these alerts to ensure that your monitoring strategy remains robust and consistent with your organizational standards. I will see you in the next session. Hello there. Let us discuss how to operationalize your data products through automated refresh schedules. This chapter focuses on transforming static reports into dynamic assets by mastering the scheduling mechanisms within the Databricks SQL interface. When we build dashboards, we are essentially creating a view into the state of our data at a specific point in time. However, business users often require this information to be updated on a predictable cadence without manual intervention. Databricks allows you to configure internal schedules for dashboards and individual queries directly through the user interface. By navigating to the schedule settings of a specific dashboard, you can define the frequency of updates. It is important to remember that these background processes consume compute resources from your assigned SQL warehouse. If you set a high-frequency refresh rate for a dashboard that performs heavy aggregations, you will observe a direct correlation in your infrastructure costs. Balancing the needs of your stakeholders for near real-time data against the fiscal reality of cloud compute spending is a fundamental responsibility of a data analyst. The configuration process is straightforward, but the architectural implications deserve careful consideration before you save your settings. When you define a schedule, you are essentially instructing the SQL warehouse to execute the underlying queries defined in your visualizations. If your dashboard consists of multiple queries, each will be triggered, which can lead to significant concurrent load on your compute resources. You should always monitor the execution time of your queries using the SQL Query Profile tool before formalizing a schedule to ensure the warehouse is appropriately sized. If a query takes 10 minutes to run and you schedule it to refresh every 5 minutes, you will quickly encounter resource contention and potential queuing. Understanding the relationship between your warehouse instance type and the complexity of your dashboard queries is essential to maintaining system stability. Managing your scheduled assets goes beyond the initial setup because failures are an inevitable part of distributed systems. Databricks provides a centralized view where you can oversee your active jobs, verify their last runtime, and inspect the status of previous executions. It is common for scheduled jobs to fail due to upstream issues, such as changes in schema, expired credentials, or data source unavailability. To mitigate the impact of these failures, you should always configure notification settings associated with your schedules. By directing these alerts to an appropriate email distribution list or webhook, you ensure that someone is informed immediately when a report goes stale. Proactive monitoring transforms your role from a reactive troubleshooter into an architect of reliable, automated data delivery pipelines. Coordinating your dashboard refreshes with the arrival of data is the final piece of the puzzle for maintaining data consistency. Many organizations rely on complex ETL or ELT pipelines that land data into your lakehouse at specific intervals during the night. If you schedule your dashboard to update before these upstream jobs complete, you are essentially presenting your stakeholders with outdated or incomplete information. You should aim to align your dashboard refresh schedules with the expected completion time of your ingestion workflows. While the interface allows you to pick static times, the ideal approach involves understanding the latency of upstream jobs and building a buffer period. By planning these schedules intentionally, you reduce the likelihood of discrepancy reports and build trust in the automated insights you provide to your organization. See you in the next lecture. Welcome to the final section focused on operationalizing your analytical work, where we explore the essential mechanisms for sharing dashboards and fostering team collaboration. In this lesson, we will examine how to manage permissions and secure data access within the Databricks environment. When you distribute a dashboard to stakeholders, the first consideration is the granularity of access control. Within Databricks, sharing is managed through specific permission levels such as can view, can run, and can manage. Granting the can view permission allows users to interact with the existing visualizations without executing the underlying queries, while can run allows users to trigger dashboard updates manually. It is prudent to adhere to the principle of least privilege, ensuring that users only possess the access level required for their specific role. By assigning permissions to groups rather than individual users, You minimize the administrative overhead and maintain a cleaner security posture as team members change over time. These assignments are managed directly within the share interface of the dashboard, which acts as the central hub for defining who can see what. An often underappreciated aspect of sharing analytical assets is the mechanism of execution, specifically distinguishing between the run as viewer and run as owner modes. When you configure a dashboard to run as owner, the queries executed to populate the dashboard use your credentials and permissions, which is highly efficient for sharing data with users who might not have direct access to the underlying tables. Conversely, the run as viewer mode forces the dashboard to execute queries using the permissions of the individual viewing the report. This is critical for compliance and security scenarios where you must ensure that users only see data they are explicitly authorized to access via Unity Catalog. Choosing between these modes shifts the burden of access control between the dashboard owner's privileges and the viewer's security profile, fundamentally altering how data governance is enforced during consumption. Beyond internal dashboard consumption, you may need to integrate your findings into broader corporate ecosystems through external sites or internal portals. Databricks provides the capability to embed visualizations by generating secure, shareable assets that can be surfaced in custom web applications. When opting for embedding, you must ensure that the authentication context is handled appropriately, as the security modes mentioned previously still apply in these external contexts. For automated scenarios where human intervention is not feasible, the Dashboard Refresh API offers a programmatic way to trigger a refresh for your data assets. This is particularly useful when you need to synchronize dashboard updates with upstream data pipeline completion, ensuring that the latest insights are available exactly when the business processes require them. Effective collaboration on analytical assets requires more than just technical permissions. It demands a structured approach to development and peer review. Treat your dashboard queries and configurations with the same rigor you would apply to application source code by utilizing version control and clear naming conventions. Before finalizing a dashboard, engage in a peer review process where colleagues inspect the logic behind your transformations and the accuracy of the visualizations. This practice not only catches potential errors in data modeling, but also ensures that the business logic represented in the dashboard remains consistent across different teams. By fostering a culture where assets are treated as collaborative products, you improve the overall quality of the artifacts and increase the trust stakeholders place in the data provided. In practice, the life cycle of a dashboard should follow a consistent path from development in a workspace to promotion into production. Always maintain a clear distinction between experimental work and shared production-ready assets to avoid polluting the workspace with outdated or incorrect reports. Regularly audit the usage of your shared dashboards to determine which assets are still providing value and which can be decommissioned, thereby keeping the environment optimized and clutter-free. Proper lifecycle management ensures that when a stakeholder navigates to a dashboard, they are viewing an authorized version that has been validated for both performance and data integrity. As you refine your skills in these collaborative workflows, you become better equipped to manage the scale and complexity inherent in modern data platforms. I will see you in the next lecture. Welcome back. In this session, we will examine the SQL Query Profile tool and learn how to extract actionable performance insights from its execution trees. When we execute a query in Databricks SQL, the engine translates our declarative SQL code into a physical execution plan that the distributed cluster must carry out. The SQL Query Profile tool provides a visual representation of this plan, turning what could be an overwhelming stream of logs into a structured tree of operators. Each node in this graphical tree corresponds to a specific step in the query lifecycle, such as scanning files, filtering data, or performing a shuffle across nodes. By observing the duration and throughput of these individual steps, you can pinpoint exactly where a query spends most of its time. High duration at a join node, for example, often suggests that the engine is struggling with memory pressure or an inefficient join strategy that requires expensive data movement across the network. Understanding these nodes is the first step in moving beyond simple trial and error optimization. One of the most critical metrics to inspect is the number of rows read by each operator versus the number of rows produced. When you see a massive disparity, specifically where an upstream operator reads millions of rows but produces very few, you have identified a bottleneck in your filtering logic. You should assess if your predicates are being pushed down to the storage layer effectively, or if your filter criteria are too weak to reduce the dataset size early in the pipeline. Furthermore, pay close attention to the shuffle size metric, which tracks how much data is being moved between worker nodes to facilitate operations like aggregations or joins. Excessive shuffling is frequently a sign that your data is not partitioned optimally, forcing the engine to redistribute data across the cluster on the fly. By minimizing the volume of data shuffled, you drastically reduce the pressure on node interconnects and shorten overall execution time. Comparing execution profiles across different SQL warehouse sizes is a powerful diagnostic technique for understanding resource consumption. If you suspect that a query is hitting memory limits on a smaller warehouse, run the same query on a larger one and compare the profiles side by side. You will often notice that the larger warehouse completes the shuffle phases faster because it has more memory allocated per node, allowing it to keep more intermediate data in RAM. However, simply throwing more hardware at a query is not always the most efficient path forward. If the profile indicates that the query is still bound by single node tasks, or if the distribution of work across nodes is skewed, then a larger cluster will yield diminishing returns. Use these comparisons to determine the cost-to-performance ratio and decide whether it is more effective to scale up your compute or to rewrite the SQL statement itself. Once you have identified an expensive operator in the profile, you should look for opportunities to rewrite the SQL to improve resource consumption, often changing the order of joins, introducing an explicit filter to restrict the dataset further, or transforming a subquery into a common table expression can alter the physical plan significantly. Some optimizations may involve reevaluating your data layout, such as ensuring your tables are clustered on frequently filtered columns to allow for partition pruning. The goal of using the query profile is to internalize these patterns so that you no longer need the tool to guess why a query is slow. Instead, you develop a mental model of how the engine interacts with Delta Lake, allowing you to write performant queries as a matter of habit. These insights into execution trees form the foundation of efficient data engineering practices within the Databricks Lakehouse. I will see you in the next lecture. Welcome back to our discussion, where today we focus on how your analytical work fits into the broader ecosystem of Databricks workflows. In this chapter, we explore workflow integration and asset lifecycle management, which are critical for transforming isolated queries into robust, production-grade automated pipelines. You will master the process of orchestrating SQL tasks, promoting assets across environments, and implementing governance through proper tagging. When we shift our perspective from ad hoc analysis to production workflows, we must view our SQL queries as components of a larger, unified architecture. Databricks Workflows allows you to string together multiple tasks, and the SQL task type is your primary vehicle for integrating SQL-based logic into these jobs. By placing a SQL task within a multitask job, you decouple the execution of business logic from the user interface, ensuring that complex transformations occur on a predictable schedule without requiring manual intervention. You define the SQL warehouse to be used for the task, which empowers you to allocate specific compute resources based on the workload requirements of the individual step rather than relying on session-based defaults. This approach not only stabilizes your data pipelines, but also allows for conditional dependencies where subsequent jobs start only after a previous query completes, thus preventing partial data corruption. The concept of an asset lifecycle implies that your analytical code, such as queries and dashboard definitions, should not live and die in a development workspace. Promoting these assets from a development environment to staging or production is a disciplined exercise in infrastructure management that relies on CI/CD principles. While individual SQL queries are text, they are often dependent on specific Unity catalog schemas, warehouse configurations, and table references that may differ across environments. To manage this lifecycle effectively, you should treat your SQL metadata and logic as code, utilizing version control systems or the Databricks CLI to migrate definitions between workspaces. By maintaining a separation of concerns between your workspace environments, you minimize the risk of executing experimental code against production tables, which is a common failure mode in organizations that lack formal promotion processes. As we mature our operational model, we must address cost visibility. which is where resource tagging becomes an indispensable utility for any data analyst. Tags are key value pairs that you apply to SQL warehouses or specific analytical assets, and they serve as metadata markers that allow for granular financial and organizational reporting. When you attach tags such as department codes or project identifiers to your resources, you enable administrators to aggregate costs and track usage patterns across different teams. This is not merely an administrative exercise. It provides the empirical data required to justify compute expenditures and identify underutilized SQL warehouses that might be contributing to wasteful cloud spend. By standardizing your tagging schema, you transform the metadata layer into a functional tool that supports organizational accountability and enables clearer insight into the lifecycle of your high-value analytical resources. Finally, the SQL task and workflows extends beyond simple execution by allowing for automated error handling and alert integration. When you configure these tasks, you can define specific failure thresholds or success criteria that trigger notifications, ensuring that stakeholders are alerted the moment a data pipeline encounters a bottleneck or an unexpected schema change. This proactive monitoring is essential for maintaining the integrity of downstream dashboard consumers who rely on consistent data freshness. By integrating these alerts into your pipeline, you shift the burden of quality control from the analyst's memory to the engine, allowing for more scalable and resilient data operations. Embracing these workflows ensures that your SQL work is integrated not just into the platform, but into the operational rhythm of the organization itself. Talk to you in the next lesson. Welcome back to the final stage of your preparation for the Databricks Certified Data Analyst Associate exam. In this session, we will synthesize the 5 core domains to ensure you are fully prepared for the certification requirements. To master this examination, you must view the Databricks Lakehouse architecture as a cohesive ecosystem, rather than a collection of isolated features. The foundation relies on Delta Lake's ACID transaction capabilities, which ensure that your data remains consistent and reliable throughout the Medallion architecture transition. When querying, your focus should remain on SQL optimization, specifically how effectively you leverage ANSI SQL, window functions, and higher order functions to manipulate complex data types. The Unity catalog serves as the primary mechanism for governance, where you define security through hierarchical access controls that manage data at the catalog, schema, table, and row levels. Understanding the difference between materialized views and standard tables is critical, as this choice directly influences storage costs and query latency. Remember that the SQL warehouse is the primary compute engine for these operations, and its selection, scaling, and serverless configuration are pivotal for performance. Finally, your visualization strategy must demonstrate clear insights through parameterized dashboards, ensuring that business stakeholders can interact with the underlying data model with minimal latency. During the exam itself, your most valuable tool is a methodical approach to reading problem statements, which often contain specific nouns indicating a particular Databricks feature. When you encounter a multi-step scenario, begin by identifying the primary limitation, such as cost constraints, performance requirements, or security compliance mandates. Apply the process of elimination by discarding answers that contradict the core Lakehouse principles, such as suggesting manual transaction management or bypassing the Unity catalog for data access. Time management is deceptive, as the exam requires a mix of theoretical knowledge and practical logical deduction. If a question feels like it is stalling your progress, mark it and move forward. You must be comfortable with the nuances of data lineage, as questions frequently ask how to trace a specific metric back to its source table via the Unity catalog. By remaining disciplined and focusing on the most heavily weighted domains like SQL manipulation and transaction logic, you will significantly improve your pass probability. The registration process requires careful attention to your technical environment, specifically concerning the requirements for online proctoring sessions. You should verify your system compatibility well before the exam date, ensuring that your software and network satisfy the standards set by the testing provider. Once you achieve certification, you have an opportunity to showcase your expertise through digital badges and linked credentials that demonstrate your proficiency with the Databricks platform. However, the ecosystem evolves at a rapid pace, so staying current involves regularly reviewing release notes and participating in technical community discussions. Keep an eye on enhancements within the SQL warehouse architecture and emerging best practices for data governance, as these are standard growth areas for the platform. Maintaining your certification status involves continuous learning, as Databricks frequently updates its product features to support modern data engineering and analytical needs. Your certification is not merely an endpoint, but a formal verification of your ability to navigate the complex lifecycle of modern data assets. See you in the next part of the series.